For most of human history, the solar system seemed simple. Not simple in size, of course. Even the distance to the nearest planet beyond Earth was vast beyond ordinary comprehension. The sun itself was enormous. The outer planets drifted through darkness at distances so great that sunlight arrived weakened and pale. Yet despite its scale, the solar system felt complete. It felt contained. There was the sun, there were the planets, and somewhere beyond them was the rest of the universe. The arrangement seemed almost intuitive, like an island surrounded by an ocean, or a campfire glowing in a dark forest. Humanity spent centuries mapping the fire. The forest remained largely unknown. Then, in 1977, two small machines began a journey that would eventually challenge one of our deepest assumptions about that boundary. Their names were Voyager 1 and Voyager 2. At the time, nobody imagined they would become detectives investigating one of the strangest regions ever explored. Their original mission was far more straightforward. A rare alignment of planets had created a fleeting opportunity. By using the gravity of giant worlds as stepping stones, the spacecraft could visit multiple planets in a single mission. It was a once-in-several-lifetimes celestial arrangement. Scientists seized the opportunity. The Voyagers launched. They flew past Jupiter, past Saturn. One continued onward. The other ventured even farther. The mission succeeded beyond expectations. They revealed volcanic worlds, frozen moons, planetary storms larger than Earth, entire landscapes no human eye had ever seen. For a while it seemed the great discoveries were behind them. The spacecraft had completed their planetary tours. The headlines faded. Public attention moved elsewhere. But Voyager kept going, year after year. Decade after decade, far beyond the planets, far beyond Pluto, far beyond the regions most people associate with the solar system. And that was when a new mystery quietly emerged, because no one knew exactly where the solar system ended. At first glance, the question sounds absurd. Surely scientists knew where the edge was. Surely maps existed. Surely there was a line. But nature rarely respects neat boundaries. The Earth has an atmosphere. Where does it end? There is no exact answer. The ocean becomes sky gradually. Day becomes night gradually. One ecosystem blends into another. The universe behaves the same way. The solar system is not enclosed by a wall. There is no fence. No border marker. No cosmic sign reading. You are now leaving. Instead, the sun continuously releases a stream of charged particles called the solar wind. This wind flows outward in every direction for billions of miles, carrying the influence of the sun far beyond the planets. Imagine smoke rising from a campfire. Close to the flames, the smoke is dense and obvious. Farther away, it spreads and weakens. Eventually, it mixes with the surrounding air. The exact moment when smoke stops being smoke and becomes atmosphere is difficult to define. The solar system faces a similar problem. The solar wind pushes outward. Meanwhile, the galaxy pushes back. Interstellar space is not empty. That fact alone would surprise many people. When most people imagine the space between stars, they picture a perfect vacuum, a vast black emptiness devoid of substance. But that image is incomplete. The darkness contains particles, atoms, magnetic fields, cosmic rays, ancient debris, invisible structures. It is not an empty void. It is a thin and ghostly environment, and it presses constantly against the expanding influence of the sun. Somewhere far beyond Pluto, these two domains meet. The solar wind pushing outward, the galaxy pushing inward. The result is something scientists call the heliosphere, a gigantic bubble inflated by the sun. For decades, researchers attempted to understand its shape. Some imagined a comet-like tail stretching behind the solar system. Others proposed a rounded structure. Some models suggested a flattened shape. Others predicted distortions caused by surrounding magnetic fields. The problem was simple. No spacecraft had ever reached the boundary. Everything remained theoretical. The heliosphere was less a map's territory than a scientific sketch, a guess drawn from incomplete evidence. Voyager changed that, slowly, quietly, year after year. The spacecraft moved farther from the sun than any human-made object in history. Its instruments continued reporting conditions from regions never before explored. Every transmission represented information from a place no human being had ever reached. Every signal carried clues. But clues to what? That question became increasingly important as Voyager approached the edge. Scientists expected certain signs. They expected the solar wind to weaken. They expected interstellar particles to increase. They expected a transition zone. What they did not expect was how confusing that transition would become. Because the closer Voyager approached the frontier, the stranger the data appeared. Measurements fluctuated. Boundaries seemed to shift. Predictions failed. Models disagreed. It was as though the edge itself refused to reveal its true nature. And then another unsettling realization emerged. Perhaps the solar system's boundary wasn't simply a border. Perhaps it was a dynamic battlefield, a constantly changing region where forces from two vastly different environments collided. If that was true, then Voyager was not merely travelling outward. It was approaching a hidden frontier. A place shaped by the interaction between our star and the galaxy beyond. A place no human instrument had ever entered. And a place that might fundamentally alter our understanding of what exists in the darkness between stars. At first, scientists believed the biggest challenge would be reaching that frontier. They were wrong. Reaching it turned out to be the easy part. Understanding what Voyager found there would become a mystery, lasting decades. And the first clue appeared when the solar wind began to fade. Long before Voyager approached the boundary of interstellar space, scientists expected to see warning signs. The solar system's protective influence could not extend forever. At some distance, the outward flow from the sun would begin to lose its strength. The solar wind would weaken. Its speed would fall. Its dominance would fade. The question was never whether this would happen. The question was when. And more importantly, what would happen next? For decades, that question remained trapped inside equations. Researchers built models. Computers generated simulations. Scientific papers proposed competing visions of the outer solar system. Yet all of them suffered from the same limitation. They were guesses. Educated guesses, certainly, but guesses nonetheless. No human-made object had ever ventured far enough to verify them. Voyager was about to change that. As the spacecraft moved farther from the sun, it entered a realm almost impossible to imagine. Distances ceased to feel meaningful. Earth became invisible. The planets disappeared behind it, one by one. Even the sun itself began to resemble an unusually bright star. If you stood beside Voyager and looked back toward home, you would not see the familiar solar system shown in textbooks. You would see a tiny point of light swallowed by darkness. The spacecraft was entering territory that had never before been explored, and the first evidence of change appeared in the solar wind. At first, the variations were subtle, small decreases, minor fluctuations, nothing dramatic. But over time, a pattern emerged. The outward flow of particles from the sun was slowing. Something ahead was resisting it. Imagine a river approaching a dam. Far upstream, the water flows normally. Closer to the obstruction, turbulence begins. Currents shift. Pressure increases. The river becomes unstable. Scientists suspected Voyager was seeing something similar on a cosmic scale. The solar wind was no longer expanding freely. It was encountering resistance from beyond. Resistance from the galaxy itself. This was a remarkable idea. For most of human history, the sun seemed overwhelmingly powerful. It dominated everything around it. It illuminated worlds, controlled planetary climates, governed the motions of entire planets. Yet here was evidence that even the sun's influence had limits. Far from home, another force was pushing back. The galaxy was not passively surrounding the solar system. It was pressing against it. And that pressure appeared stronger than expected. But how strong? And what exactly was pushing? Those questions soon led scientists toward one of the strangest regions in the solar system, a region known as the termination shock. The name sounds violent. In reality, it describes a hidden frontier where the solar wind abruptly slows down. Not because the sun weakens, but because the environment ahead becomes increasingly difficult to penetrate. The analogy is simple. Imagine a jet aircraft flying faster than sound. As it moves, pressure builds ahead of it. A shockwave forms. Something similar occurs at the outer reaches of the solar system. The solar wind races outward at enormous speeds. Eventually, it encounters enough opposition that it can no longer maintain its momentum. The flow slows dramatically. The conditions change. A shock forms. Scientists had predicted this region for years. But prediction is one thing. Observation is another. Voyager was approaching it directly. Then, in the early 2000s, the data began to reveal something remarkable. The spacecraft detected evidence that it was nearing the termination shock. Measurements changed. Particle behavior shifted. The environment became increasingly turbulent. It was working. The theories appeared correct. After decades of uncertainty, researchers were finally watching a prediction come true. For a moment, it felt like the mystery was being solved. The solar system had a structure. Voyager was confirming it. The boundary was behaving roughly as expected. The story seemed straightforward. Then, the data became strange. Very strange. The termination shock did not appear where many models predicted. The conditions fluctuated unexpectedly. Its location seemed to move, sometimes closer, sometimes farther away. The boundary behaved less like a wall and more like a living thing. A breathing thing, expanding and contracting as solar activity changed. This created a troubling possibility. If the termination shock itself could move, then perhaps every outer boundary of the solar system was more dynamic than scientists had imagined. The neat diagrams in textbooks suddenly looked suspiciously simple. Reality appeared messier, much messier, and Voyager kept finding clues. One of the strangest involved energetic particles. Researchers expected certain behaviors as the spacecraft approached the outer frontier. Instead, some particles appeared in surprising locations. Others vanished unexpectedly. Some seemed trapped. Others escaped. The patterns did not fit neatly into existing theories. Why? What invisible structures were influencing them? What hidden forces shaped their paths? Nobody knew. The mystery deepened. Then came an unsettling realization. Perhaps scientists had misunderstood the outer solar system entirely. For years, many researchers imagined the heliosphere as a relatively stable bubble, a protective shell surrounding our planetary neighborhood. But Voyager's observations hinted at something more complicated, something more chaotic. The boundary regions seemed active, dynamic, restless. Instead of a quiet border, they resembled a weather system, an environment constantly changing in response to forces from both the Sun and the galaxy. This had enormous implications, because the heliosphere is more than a boundary. It is a shield, a vast protective cocoon that helps block dangerous cosmic radiation. Without it, Earth would exist in a much harsher environment. Life itself might face very different conditions. Understanding the heliosphere was not merely an academic exercise. It was part of understanding why our corner of the galaxy is habitable at all. And Voyager was revealing that this shield was far more complicated than expected. Yet an even greater mystery was approaching. As the spacecraft continued outward, it entered regions where the solar wind slowed dramatically, then slowed even more. Eventually, scientists realized they were witnessing something extraordinary. The outward flow from the Sun was nearly stopping, not disappearing entirely, but losing the dominance it had maintained for billions of miles. For the first time in history, humanity was approaching the point where another environment would begin to take control. The realm beyond the Sun, the realm between the stars. Researchers anticipated a clear transition, a moment of crossing, a scientific milestone that could be identified instantly. But nature had other plans, because when Voyager finally approached the invisible frontier, everyone had been waiting for the evidence, refused to agree. Some instruments suggested the crossing had happened, others suggested it had not. Some data pointed toward interstellar space, other data pointed back toward the solar system. It seemed impossible. How could a spacecraft be both inside and outside at the same time? The answer would trigger one of the most controversial debates in modern space science, and it would transform a simple boundary crossing into a mystery that remains unresolved even today. For years, scientists imagined the moment, the crossing. The instant when a human-made object would leave the solar system and enter the space between the stars. It sounded like the kind of milestone history would recognize immediately, like landing on the moon. Like breaking the sound barrier, like seeing Earth from orbit for the first time. There would be a date, a location, a definitive answer. Humanity would know exactly when it happened. That was the expectation. Reality turned out to be far stranger. By the late 2000s, Voyager 1 was moving through a region unlike anything it had previously encountered. The solar wind had weakened dramatically. Particle measurements were changing. The spacecraft appeared to be approaching the long-anticipated frontier. Researchers watched closely. Every transmission carried new evidence. Every signal was examined for clues. The excitement was understandable. This was not merely another milestone in planetary exploration. Voyager was approaching a place no human instrument had ever reached. The first direct encounter with interstellar space. Or so it seemed. Then, something unexpected happened. The spacecraft entered a region that scientists would later describe using an oddly ordinary phrase. The magnetic highway. The name sounds harmless. Almost mundane. But the discovery behind it created enormous confusion. Suddenly, Voyager began detecting dramatic changes in particle populations. Certain energetic particles originating from within the heliosphere began disappearing. At the same time, particles arriving from outside the solar system surged. The shift was dramatic. One population collapsed. Another appeared. To many researchers, the conclusion seemed obvious. Voyager had crossed the boundary. The mystery was solved. The spacecraft had entered interstellar space. News headlines began to appear. Excitement spread. Humanity had finally reached the stars. Except there was a problem. One instrument disagreed, and that disagreement changed everything. Scientists expected the crossing to produce a clear magnetic signature. Inside the heliosphere, magnetic fields associated with the Sun dominate. Outside, interstellar magnetic fields should behave differently. Researchers anticipated a noticeable change in direction, a cosmic compass needle swinging toward a new orientation. The expected shift never appeared. Voyager's magnetic field measurements remained stubbornly similar. The data refused to cooperate. If the spacecraft had entered interstellar space, why hadn't the magnetic field changed as predicted? The contradiction created immediate controversy. Some scientists argued the crossing had occurred. Others insisted it had not. Both sides possessed evidence. Both sides had legitimate arguments. The boundary seemed to exist in two contradictory states simultaneously. The situation resembled a detective story in which every clue pointed toward a different suspect. The particles suggested one answer. The magnetic field suggested another. Which evidence should be trusted? The debate intensified. Then things became even stranger. Researchers began re-examining assumptions they had held for decades. Perhaps the boundary itself was different than expected. Perhaps interstellar space did not begin with a sharp transition. Perhaps the magnetic fields on either side were more closely aligned than anyone had imagined. A possibility emerged, one that few researchers had seriously considered before. What if the boundary between the solar system and interstellar space was not a wall? What if it was more like a coastline? Think of standing on a beach during high tide. Where exactly does the ocean end? Where exactly does the land begin? The answer changes from moment to moment. Waves advance. Waves retreat. The boundary shifts continuously. Perhaps Voyager had entered a similar region, a place where two environments overlapped, a place where solar influence and galactic influence mixed together, a place where simple definitions failed. The idea was unsettling. Human beings prefer clear categories. Inside, outside, here, there. But nature often ignores such distinctions. The deeper scientists looked, the more complicated the frontier appeared. Then, in 2012, the evidence reached a turning point. Voyager observed a dramatic and sustained increase in galactic cosmic rays. At the same time, particles associated with the heliosphere dropped sharply. Unlike previous fluctuations, these changes persisted. Weeks passed. Months passed. The pattern remained. The signal appeared genuine. Something fundamental had changed. Many researchers concluded that Voyager had indeed entered interstellar space. Eventually, this interpretation gained broad acceptance. The official crossing date became August 25, 2012. Humanity had reached the space between stars. Case closed, or so it seemed. But this would become the first major false ending in the story, because solving one mystery exposed another, a much larger one. What exactly had Voyager entered? The popular image was simple. The spacecraft had left the solar system. Beyond lay empty space, darkness, nothingness, an immense vacuum stretching between distant suns. That picture quickly began to collapse. The data showed something very different. The environment beyond the heliosphere was not empty, not even close. Instead, Voyager detected a region filled with particles, magnetic fields, pressure gradients, invisible structures. The darkness possessed texture. It possessed architecture. It possessed history. The discovery challenged one of humanity's oldest assumptions. For centuries, space between stars had been treated as absence, the empty stage upon which galaxies and stars existed. Voyager suggested the opposite. The darkness was not merely background, it was a physical environment, an active environment, perhaps even a dynamic one. Imagine discovering that the blank spaces on a map were not blank at all. Imagine learning that an unexplored desert contained hidden rivers, buried cities, and forgotten roads. That was the scale of the revelation. The space between stars was becoming a place, a real place. And like every place, it contained mysteries. Questions multiplied. What created the particles surrounding Voyager? Why were densities higher than expected? How did magnetic fields behave there? What hidden structures existed beyond the heliosphere? Most importantly, what could these observations reveal about the galaxy itself? Voyager had been designed to study planets. Now it was investigating an entirely different subject, the environment between stars, an environment that remained largely invisible from Earth. And the spacecraft possessed one extraordinary advantage. It was inside the mystery. Every day, Voyager travelled farther into a realm no human being had ever explored. Every transmission represented direct evidence from a hidden frontier. The spacecraft had crossed the invisible wall, but instead of finding answers, it discovered something more unsettling. The wall itself was only the beginning, because beyond it lay a darkness that was not dark at all, and buried within that darkness were signals nobody expected to hear. For generations, the darkness between the stars occupied a peculiar place in the human imagination. It was often described using the language of absence, empty, silent, dead, a vast gulf separating islands of light. Stars were the important things, planets were the important things, galaxies were the important things. Everything in between was treated almost as an afterthought, a black backdrop, a cosmic blank page. Voyager was beginning to reveal how misleading that picture truly was, because once the spacecraft moved beyond the sun's protective bubble, something unexpected emerged from the darkness. Not light, not matter visible to the eye. Something stranger, a hidden form of sound. Of course, sound cannot travel through the vacuum of space in the ordinary sense. There are no air molecules carrying vibrations from one place to another. The familiar sounds of Earth, thunder, music, voices cannot cross interplanetary distances. Yet the environment surrounding Voyager was not a perfect vacuum. It contained particles, extremely sparse particles, far fewer than even the emptiest laboratory chamber ever created on Earth, but not zero. And where particles exist, vibrations can exist. The discovery began with an event occurring billions of miles away, an eruption from the sun, one of the largest ever observed. In 2012, powerful solar activity launched enormous shockwaves outward through the solar system. These disturbances travelled for months, then years. Eventually, they reached Voyager. What happened next surprised everyone. The spacecraft detected oscillations in the surrounding plasma, tiny vibrations moving through the thin gas of interstellar space. Scientists converted the measurements into audible frequencies. For the first time, humanity effectively listened to the environment between the stars. What they heard sounded eerie, haunting, like a distant whistle echoing through an abandoned structure, a ghostly tone buried within the darkness. The public often described these recordings as the sounds of interstellar space. Strictly speaking, they were translations of plasma vibrations. But the distinction almost missed the deeper point. The important discovery was not the sound itself. The important discovery was what the sound revealed. The darkness wasn't silent. It contained structure. The vibrations allowed scientists to measure the density of the surrounding plasma, and the results created a new mystery. The density was unexpectedly high, much higher than many researchers anticipated. This was strange. Very strange. For decades, models of the heliosphere suggested one set of conditions. Voyager was reporting another. Imagine leaving a city and entering what you believe is an empty wilderness. Instead of finding emptiness, you discover roads, buildings, evidence of hidden activity. That was the feeling among researchers. Interstellar space appeared more substantial than expected, more populated, more complex. But why? Where was this material coming from? What processes maintained it? And how representative was Voyager's location? These questions quickly transformed a single measurement into a larger investigation. Scientists began examining the local interstellar medium, the environment surrounding our solar system. The term sounds technical. The reality is fascinating. Our sun is not drifting through a random region of the galaxy. It occupies a particular neighborhood, a specific patch of interstellar space. Just as Earth exists within a continent, and a continent exists within a planet, the solar system exists within larger cosmic environments. And like neighborhoods on Earth, these regions have histories. Some are calm, some are turbulent, some bear scars left behind by ancient events. Voyager's data hinted that our local neighborhood might possess such scars. Perhaps the density measurements reflected remnants of ancient stellar explosions. Perhaps they represented compressed material shaped by long-forgotten forces. The clues were incomplete, but a possibility emerged. The darkness surrounding Voyager was not merely present-day space. It might be a historical archive, a record of events that occurred millions of years ago, a fossil preserved across interstellar distances. The idea was extraordinary. Imagine walking through a forest and realizing every tree contains evidence of forgotten civilizations, that every stone preserves traces of vanished worlds. Voyager was beginning to reveal something similar. The region between stars appeared to carry memories, not conscious memories, physical memories, remnants of ancient processes still visible today. And those remnants were speaking through plasma vibrations. Yet another mystery soon appeared. The density measurements did not remain perfectly constant. Changes emerged, subtle variations. Different regions appeared to possess different characteristics. The interstellar medium was not uniform. It had texture, layers, Structure. This realization challenged another long-standing assumption. Scientists had often described interstellar space as diffuse, thin, featureless. Voyager suggested otherwise. The darkness resembled weather more than emptiness, a landscape rather than a void. Invisible rivers might flow through it. Invisible boundaries might divide it. Invisible storms might shape it. But how could such structures exist in a region so sparse? That question became increasingly important, because understanding these hidden features would require understanding something even more mysterious. Magnetic fields. Unlike stars or planets, magnetic fields cannot be seen directly. They reveal themselves only through their effects. Yet throughout the universe, they play a surprisingly powerful role. They guide particles, shape cosmic structures, influence the movement of matter across enormous distances. In many ways, magnetic fields act like invisible architecture, frameworks hidden beneath reality. Voyager's observations hinted that such architecture existed throughout interstellar space. The darkness was not random. Something was organizing it. Something was giving it form. But what? And how extensive were these structures? No one knew. Then researchers realized the implications extended far beyond the local neighborhood. If interstellar space contained hidden architecture, then the galaxy itself might be connected by enormous magnetic networks, vast structures spanning distances difficult to comprehend. The scale shift was staggering. What began as a question about Voyager's surroundings was becoming a question about the Milky Way. The investigation was growing larger. Again, that pattern would repeat many times. Every answer seemed to uncover a bigger mystery. Every discovery expanded the scope of the investigation. At first, scientists wanted to know whether Voyager had left the solar system. Now they were asking how the galaxy itself was structured. The frontier kept moving, and Voyager kept traveling farther into darkness, farther into territory no human instrument had ever explored. The spacecraft had revealed that the silence between stars was not silent. It contained vibrations, density, structure, history. But the most surprising clue had not yet emerged, because hidden within the darkness was evidence that our entire solar system might be moving through the remnants of an ancient cosmic catastrophe, and the scar left behind was larger than anyone imagined. The deeper Voyager travelled into interstellar space, the more an uncomfortable truth emerged. Humanity had spent centuries studying stars. We had mapped planets, measured galaxies, tracked black holes. Yet we knew remarkably little about the medium connecting all of them. It was as if explorers had carefully documented every island in an ocean, while remaining almost completely ignorant of the water itself. Voyager was changing that, and the first clues came not through images, but through vibrations. The spacecraft could not photograph the darkness around it. There were no nearby worlds to illuminate, no dramatic landscapes, no towering storms. Only an invisible environment stretching in every direction. Yet hidden within that apparent emptiness was a continuous flow of information. The challenge was learning how to read it. Scientists soon realized that the plasma oscillations detected by Voyager were more than curiosities. They were tools. Powerful tools. Much like seismologists use earthquakes to study Earth's interior, researchers could use plasma vibrations to probe interstellar space itself. A new method of exploration emerged, not by seeing, but by listening. Imagine standing in a dark cave. Your flashlight has failed. You cannot see the walls. You cannot see the tunnels, but you can shout. And from the returning echoes, you begin to reconstruct the hidden landscape. That was essentially what Voyager was doing. The spacecraft wasn't generating the echoes. The sun was. Solar eruptions launched shockwaves outward through the heliosphere and beyond. When those disturbances passed Voyager, they triggered oscillations in the surrounding plasma. The resulting echoes revealed properties of the unseen environment. For the first time, humanity could investigate the darkness between stars directly, and the darkness had a story to tell. The earliest measurements suggested that Voyager occupied a surprisingly dense region of interstellar space. Not dense by earthly standards, of course. The environment remained extraordinarily sparse. A cubic centimetre contained only a tiny number of particles, but relative to expectations, the numbers were significant. Something about the local interstellar medium appeared unusual. The discovery sparked immediate debate. Perhaps existing models were incomplete. Perhaps Voyager occupied an exceptional location. Or perhaps something larger was happening. The third possibility proved particularly intriguing, because when scientists expanded their perspective, a strange pattern emerged. The solar system does not stand still. It moves. The Sun orbits the center of the Milky Way. As it travels, it passes through different regions of the galaxy, different environments, different conditions, different histories. Earthly analogies help. Imagine driving across a continent. The landscape changes. Forests become deserts. Mountains become plains. Weather shifts. Vegetation changes. The same journey occurs on a galactic scale. Over millions of years, the solar system drifts through various interstellar environments, and Voyager's measurements suggested that our current neighborhood might be anything but ordinary. Researchers began investigating the possibility that the Sun was traveling through a region shaped by ancient stellar explosions, supernovae, the deaths of massive stars. These events were among the most violent phenomena in the universe. For a brief moment, a single exploding star can outshine entire galaxies. The blast waves expand outward for millions of years. They compress gas, shape magnetic fields, carve enormous cavities into interstellar space. Their influence persists long after the original star has vanished. Could Voyager be detecting evidence of such events? The possibility was difficult to ignore, because our region of the galaxy already possessed a suspicious feature. Astronomers call it the local bubble. The name sounds harmless, almost whimsical. In reality, it describes something enormous. The local bubble is a vast cavity in interstellar space surrounding the solar system. Its dimensions are staggering. Hundreds of light years across, large enough to contain countless star systems. Yet compared to neighbouring regions, it contains relatively little dense gas. Something appears to have cleared it out. Something powerful. For years, astronomers suspected a series of ancient supernovae, multiple stars exploding over millions of years. Their combined shockwaves may have excavated this enormous cavity. If true, the solar system exists inside the remnants of long-forgotten cosmic violence. A survivor drifting through an ancient womb. Voyager's measurements seemed consistent with this picture, but consistency is not proof. The evidence remained incomplete, and that incompleteness generated new questions. How many supernovae created the local bubble? When did they occur? How close were they? Did they influence Earth's history? Could traces of those explosions still be reaching us today? The deeper scientists investigated, the stranger the story became. Evidence began appearing from entirely different fields: ocean sediments, radioactive isotopes, geological records. Some studies suggested that debris from ancient supernovae had actually reached Earth. Not recently, millions of years ago, tiny traces preserved in rocks and sediments. Physical evidence that exploding stars once affected our cosmic neighborhood. The implications were extraordinary. The darkness surrounding Voyager might not simply be a location. It might be a historical artifact, a surviving remnant of events that occurred long before humanity evolved, long before mammals dominated Earth, long before the first human ancestor looked toward the sky. The spacecraft was traveling through ancient history. History written not in books, but in particles and magnetic fields. And like any historical investigation, each clue generated new mysteries. One question became especially important. If ancient supernovae helped shape our local environment, what effect did they have on interstellar space itself? The answer appeared to involve magnetic fields again. Researchers noticed that magnetic structures seemed deeply connected to the distribution of matter surrounding the solar system. The two could not be understood separately. Matter influenced magnetic fields. Magnetic fields influenced matter. Together, they formed an invisible framework, a hidden architecture guiding the behavior of interstellar space. The analogy was simple. Imagine iron filings scattered across a table. Without a magnet, they appear random. Place a magnet beneath the surface, and suddenly patterns emerge. Invisible forces create visible order. Voyager was beginning to reveal something similar on a galactic scale. The darkness was not random. It was organized, shaped, structured. The unseen ocean between stars possessed currents, boundaries, and perhaps even pathways. That possibility carried enormous implications, because if particles could follow hidden magnetic routes through the galaxy, then information about distant events might travel farther and more efficiently than previously believed. Ancient stellar explosions, cosmic rays, interstellar matter, everything might be connected through invisible channels. The idea seemed almost elegant. For a moment it appeared the mystery might be approaching a solution. The local bubble explained the density. Ancient supernovae explained the history. Magnetic structures explained the organization. The pieces seemed to fit. Then another anomaly appeared, one that threatened to unravel the entire picture. Because the magnetic field surrounding Voyager refused to behave the way scientists expected, and the more carefully they measured it, the more mysterious it became. At first, the numbers looked reassuring, not exciting. Not revolutionary, just reassuring. Scientists had spent years trying to understand the environment beyond the heliosphere. They had built models, tested assumptions, and argued over competing interpretations. When Voyager began transmitting density measurements from interstellar space, many researchers expected confirmation, a chance to compare prediction against reality, a chance to refine the map. Instead, the map began to fall apart. The problem was subtle at first. Voyager's plasma measurements repeatedly suggested that the density of the surrounding interstellar medium was higher than anticipated. Not impossibly high, not enough to overturn physics, but high enough to create discomfort, high enough to suggest that something important had been overlooked. And in science, small discrepancies often conceal large mysteries. History is full of examples. The orbit of a planet seems slightly wrong. A faint signal appears where none should exist. A measurement refuses to match expectations. At first, the anomaly appears insignificant. Then, the anomaly survives scrutiny. Then it grows. Eventually, scientists realize they are not looking at an error. They are looking at a clue. Voyager's density measurements felt increasingly like that kind of clue. The question was simple. Why was the space between stars denser than expected? The answer was not. Researchers initially suspected local effects. Perhaps Voyager happened to occupy an unusually dense pocket of interstellar material. Perhaps the spacecraft had entered a temporary structure, a cloud, a filament, a concentration of gas. Such structures exist throughout the galaxy. Interstellar space is not uniform. Some regions contain more matter than others. The explanation seemed reasonable, but there was a problem. As additional measurements accumulated, the anomaly persisted. The numbers refused to disappear. The surrounding environment consistently appeared more substantial than many models predicted. The mystery deepened. Scientists began looking beyond Voyager itself. What if the problem wasn't local? What if the assumptions about our galactic neighborhood were incomplete? That possibility forced researchers to revisit one of astronomy's most important questions. What exactly is the interstellar medium? The phrase sounds technical, but the concept is surprisingly simple. Between stars lies matter. Extremely thin matter, gas, dust, charged particles, magnetic fields, not enough to resemble clouds or atmospheres, yet enough to shape the evolution of galaxies. Without the interstellar medium, stars could not form, planets could not emerge, galaxies would look fundamentally different. The space between stars is not merely empty territory, it is the raw material from which future stars are born, a kind of cosmic reservoir. Voyager was exploring the nearest portion of that reservoir, and the results suggested it might be richer and more structured than expected. The implications extended far beyond our solar system, because if the local interstellar medium was denser than anticipated, then many existing models might require revision. Researchers compared the situation to discovering that an ocean was deeper than previously measured. The difference might seem small at first, but depth influences currents. Currents influence climate. Climate influences ecosystems. A single measurement can cascade through an entire system of understanding. The same principle applied here. Density affects pressure. Pressure affects magnetic fields. Magnetic fields affect particle transport. Everything was connected, and the connections were becoming increasingly complicated. Then another clue emerged. The density measurements appeared linked to something even more mysterious. Cosmic rays. These particles had already begun attracting attention. Voyager was detecting them in remarkable numbers. Unlike ordinary particles carried outward by the solar wind, cosmic rays originate from far beyond the solar system. Some travel across enormous portions of the galaxy. Others may have originated in distant stellar explosions. Many carry astonishing amounts of energy. They are among the fastest particles in nature, and they possess a peculiar characteristic. Their behavior depends heavily on the environment through which they travel. Density matters. Magnetic fields matter. Structure matters. The higher than expected densities surrounding Voyager might help explain certain cosmic ray observations, at least partially. For a moment, researchers felt they were closing in on an answer. The pieces appeared to fit. Interstellar density influenced cosmic ray transport. Ancient supernovae shaped local conditions. Magnetic fields organized the environment. The mystery seemed manageable. Then reality complicated everything again, because cosmic rays were not behaving perfectly either. Some arrived in surprising quantities. Others appeared suppressed. Certain energy ranges displayed unexpected patterns. The data hinted that something invisible was influencing their movement, something beyond simple density alone. The situation resembled investigating traffic patterns in a city. Knowing the number of vehicles helps, but it doesn't explain everything. Road networks matter. Traffic signals matter. Hidden bottlenecks matter. Without understanding the underlying structure, the observations remain incomplete. Scientists increasingly suspected a similar situation in interstellar space. Density was only part of the story. The deeper mystery involved architecture, invisible architecture. Magnetic architecture. Voyager's measurements suggested that particles did not simply drift randomly through the galaxy. Instead, they appeared guided, directed, constrained, as though hidden pathways existed within the darkness. The idea transformed how researchers viewed interstellar space. Rather than an empty void sprinkled with particles, it began to resemble a landscape. Not a visible landscape, an invisible one, a terrain shaped by magnetic forces. Imagine flying above a forest at night. The trees are hidden, the rivers are hidden, the roads are hidden. Yet, if you watch the movement of light below, patterns emerge. Vehicles follow routes. Water follows channels. Activity reveals structure. Cosmic rays were behaving in much the same way. Their movements hinted at unseen frameworks beneath the darkness, and those frameworks seemed far larger than anyone expected. The scale escalation was breathtaking. What began as a question about Voyager's immediate surroundings was becoming a question about the organization of the Milky Way itself. How extensive were these magnetic structures? How long did they persist? What created them? No definitive answers existed, only clues. And every clue pointed toward increasing complexity. The darkness between stars was not becoming simpler as Voyager traveled deeper into it. It was becoming richer, layered, more interconnected, almost alive with hidden processes. The spacecraft had already challenged the idea of empty space. Now it was challenging the idea of randomness. Patterns were emerging. Invisible order was emerging. Yet one piece of evidence remained especially difficult to explain, because alongside the unusual densities and mysterious particle behavior Voyager appeared to be moving through, a region marked by the remnants of ancient violence. Not recent violence, not events occurring thousands of years ago, but scars left behind millions of years in the past. Scars so vast they stretched across interstellar distances, and understanding those scars would require investigating a forgotten chapter in the history of our galactic neighborhood, a chapter written by stars that no longer exist. Most scars eventually fade. A wound heals, the evidence softens, time erases the details. The universe operates differently. Its scars can survive for millions of years, sometimes hundreds of millions. Long after the original event has vanished, traces remain scattered across space. Invisible fingerprints, ghostly remnants. Echoes of violence preserved within the fabric of the galaxy. As Voyager moved deeper into interstellar space, scientists began to suspect that the spacecraft was travelling through one of those scars, not a small one, not a local feature, a structure so enormous that it encompassed the entire solar system, and perhaps much more. The idea emerged gradually. No single measurement proved it. Instead, clues accumulated. Density measurements, particle behaviour, magnetic field observations. Astronomers studying entirely different regions of the sky began noticing patterns that seemed connected. Slowly, a picture started to form. Our cosmic neighbourhood had a history, a violent history. To understand it, researchers had to think on timescales that dwarfed human civilization. Thousands of years would not be enough, neither would tens of thousands. The story stretched back millions of years to a time before modern humans existed, before ice ages reshaped Earth, before many familiar species evolved. The protagonists of this forgotten story were stars, massive stars, the giants of the galaxy. These stars live fast and die young. Unlike the Sun, which will survive for billions more years, massive stars burn through their fuel rapidly. They shine intensely. They evolve quickly. And eventually, they explode. When they do, the consequences are extraordinary. A supernova releases unimaginable amounts of energy. Shock waves race outward through space. Matter is hurled across interstellar distances. Entire regions of the galaxy can be transformed. One supernova is significant. Several occurring in the same region can reshape vast areas of space. Astronomers increasingly suspected that something like this had happened near the solar system. Not recent, millions of years ago. Multiple stars may have exploded in succession, each eruption driving powerful shockwaves through the surrounding interstellar medium. Over time, those shockwaves could have excavated an enormous cavity, a bubble, the local bubble. For years, the local bubble remained a useful but somewhat abstract concept. Astronomers knew it existed. Observations suggested a large, relatively low-density region surrounding the solar system, but its origins remained uncertain. Voyager's discoveries began giving the bubble a story, a history, a possible explanation. The darkness surrounding the spacecraft no longer looked random. It looked shaped, as though enormous forces had passed through long ago. Imagine walking through an ancient battlefield. The soldiers are gone, the weapons are gone, The cities may have vanished, yet subtle traces remain. Earthworks, fragments, patterns in the landscape, evidence that something significant occurred there. Voyager appeared to be exploring the cosmic equivalent. The spacecraft was moving through a region moulded by events long since completed. The original stars were gone, but their influence remained, and the scale was astonishing. The local bubble spans hundreds of light years. To appreciate that size, consider this. Light itself, the fastest thing in the universe, requires centuries to cross it. Entire civilizations could rise and fall while a beam of light travels from one side to the other, and yet this immense structure may have been created by a series of stellar deaths. The implication was profound. The environment surrounding the solar system was not merely a backdrop, it was the product of history, ancient history. The realization changed how scientists viewed Voyager's mission. The spacecraft was no longer simply measuring present conditions, it was investigating a fossil, a surviving remnant of events millions of years old. Every density measurement became historical evidence. Every particle count became a clue. Every magnetic observation became part of a reconstruction. The mission had become archaeology on a galactic scale. And like all archaeology, it raised new questions. How many supernovae contributed to the local bubble? 2, 10, 20. Researchers proposed different answers. Some models suggested a cluster of massive stars that lived and died relatively close together. Others envisioned multiple generations of stellar explosions. The exact number remained uncertain, but most scenarios shared a common theme. The solar system exists within the aftermath of ancient destruction. That conclusion carried an unsettling implication. If supernovae shaped our local environment in the past, could they affect us again in the future? The answer was uncomfortable. Yes, the galaxy is not static. Stars continue to form. Stars continue to die. Eventually, future explosions will occur somewhere in the Milky Way. Most will be too distant to matter. Some might not be. The realization transformed the local bubble from a historical curiosity into something more personal. The environment surrounding Earth exists because of ancient stellar events. Life evolved within conditions partially shaped by long-dead stars. The connection was intimate. The history of the galaxy and the history of Earth were intertwined. But the mystery was not finished, because evidence began appearing from an unexpected source: Earth itself. Researchers studying ocean sediments discovered traces of radioactive isotopes that should not naturally exist in significant quantities. One isotope attracted particular attention: iron-60. This material is produced in supernova explosions. It decays over time. Finding it on Earth suggested something remarkable. At some point in the distant past, debris from nearby supernovae may have reached our planet, not metaphorically, literally. Particles created in exploding stars may have drifted across interstellar space and settled into Earth's oceans. The implication felt almost unbelievable. The same events that helped shape the local bubble may have left traces beneath our feet. The evidence remained incomplete. Scientists debated interpretations. Alternative explanations existed, yet the possibility was difficult to ignore. The boundary between astronomy and geology was beginning to blur. The history of the galaxy appeared written into Earth's own record. Voyager's observations were contributing to a story far larger than anyone anticipated, a story linking exploding stars, interstellar space, and life on Earth. For a moment, it seemed the mystery might finally be coming together. The local bubble explained the unusual environment. Ancient supernovae explained the scar. The fossil record provided supporting evidence. The pieces appeared increasingly coherent. Another false ending seemed within reach. Then a stubborn problem refused to disappear: the magnetic field again. No matter how well the supernova explanation accounted for certain observations, Voyager's magnetic measurements continued raising uncomfortable questions that would become impossible to ignore. Because the invisible architecture surrounding the spacecraft appeared far stranger than anyone had imagined, and understanding it would force scientists to reconsider one of their most confident assumptions about the edge of the solar system. By this point in the investigation, scientists felt they had assembled a reasonable story. Voyager had crossed beyond the heliosphere. The spacecraft was measuring interstellar plasma. The surrounding environment bore signs of ancient supernova activity. The local bubble provided a historical framework. The pieces appeared increasingly connected, not perfectly, but sufficiently. Many researchers believed the central mystery was nearing resolution. Then the magnetic field refused to cooperate again. The problem was surprisingly simple to describe. For decades, scientists expected the boundary between the solar system and interstellar space to reveal itself through magnetism. The logic seemed straightforward. Inside the heliosphere, the sun's magnetic influence dominates. Outside the galaxy's magnetic environment should take over. The transition ought to be noticeable. Imagine sailing from one ocean current into another. The water still looks like water, but the flow changes. The direction changes. The behavior changes. Researchers expected a similar shift when Voyager crossed into interstellar space. The magnetic field should rotate, not necessarily dramatically, but enough to identify the transition, enough to announce that a new environment had begun. That was the prediction. Voyager delivered something else. The particle data looked convincing. Cosmic rays increased. Solar particles declined. Plasma densities matched expectations for interstellar space. Everything pointed toward a successful crossing. Everything except the magnetic field. Instead of rotating sharply, the field remained unexpectedly aligned with the heliospheric direction. The cosmic compass barely moved. The result created immediate confusion. Had Voyager truly entered interstellar space? Or was it trapped in some transitional zone, a kind of borderland between environments? The debate spread quickly. Scientists found themselves divided into competing camps. One group emphasized particle evidence. Another emphasized magnetic evidence. Each side possessed legitimate arguments. Each side could point to real observations. The situation resembled a courtroom where two witnesses tell contradictory stories. Both appear credible. Both appear honest, yet their accounts cannot simultaneously be correct. Some researchers argued that the crossing simply had not occurred. The spacecraft remained inside the heliosphere, perhaps near the boundary, perhaps extremely near, but still inside. Others disagreed. The particle data seemed overwhelming. If Voyager was not in interstellar space, where were the cosmic rays coming from? Why had solar particles vanished? Why had plasma densities changed so dramatically? The evidence seems too strong to dismiss. The mystery deepened. Then a more radical possibility emerged. Perhaps the assumptions themselves were wrong. Not the measurements, not the instruments. The assumptions. What if scientists misunderstood the structure of the boundary? This possibility forced researchers to reconsider decades of theoretical work. Perhaps the heliosphere and interstellar medium interacted in more complex ways than expected. Perhaps magnetic fields could connect across the boundary. Perhaps the transition was not abrupt at all. The idea felt uncomfortable. Human beings naturally imagine borders as sharp divisions. A fence separates two properties. A shoreline separates land from sea. A wall separates one room from another. Nature often prefers gradients, landing zones, intermediate states. The more closely scientists examined Voyager's observations, the more they suspected the heliopause, the boundary between solar and interstellar influence, might behave that way. Instead of a wall, it might resemble woven fabric, threads from one environment intertwining with threads from another. The analogy proved useful. Imagine two rivers meeting. The water from each river does not stop instantly. Currents mix. Whirlpools form. Channels intertwine. The boundary exists, yet remains difficult to define precisely. Perhaps Voyager occupied a similar region, a place where solar magnetic fields and interstellar magnetic fields interacted directly. A place where categories became unreliable. The possibility transformed the mystery. The question was no longer simply whether Voyager had crossed the boundary. The question became, what kind of boundary was it? That distinction mattered enormously, because boundaries determine how particles move, how energy flows, how cosmic rays enter the solar system, how the heliosphere protects Earth. Understanding the frontier meant understanding our cosmic shield. And that shield influences the conditions under which life exists. The stakes were larger than they first appeared. Then another clue arrived. Computer simulations improved. New models incorporated Voyager's observations. Researchers began exploring scenarios in which interstellar magnetic fields draped themselves around the heliosphere. The image was striking. Imagine water flowing around a submerged rock. The flow bends, wraps around the obstacle, creates patterns that reflect the object's shape. Some scientists proposed that interstellar magnetic fields behaved similarly. As the solar system moved through the galaxy, magnetic fields could become distorted around the heliosphere. This would naturally align certain field directions. The missing rotation might not be mysterious at all. It might be expected. At first glance, the explanation seemed elegant, perhaps too elegant, because every solution generated new questions. If magnetic draping occurred, how extensive was it? How stable was it? Did it affect cosmic ray transport? Could it explain other anomalies? Researchers found themselves solving one mystery, only to uncover several more. The pattern was becoming familiar. Every apparent answer enlarged the investigation. Every breakthrough revealed deeper complexity. The universe refused to provide simple conclusions. Then came another complication: Voyager 2. For years, Voyager 1 had dominated attention because it travelled faster and reached the boundary first. But Voyager 2 followed a different path through the outer solar system. A different route meant different observations. A second witness. And second witnesses are invaluable in detective stories. Sometimes they confirm the testimony. Sometimes they expose flaws. Scientists eagerly awaited what Voyager 2 would find. If its observations matched Voyager 1, confidence would increase. If they differed significantly, new mysteries would emerge. When the data eventually arrived, researchers received a mixture of both. Some features appeared familiar, others did not. The heliosphere was beginning to look asymmetrical, uneven, shaped by forces more complicated than anyone anticipated. The frontier was not a perfect sphere. It was something stranger. Something sculpted by interactions occurring across enormous scales. For a moment it seemed the investigation had reached a satisfying explanation. The boundary was complex. Magnetic fields intertwined. Ancient supernovae shaped the local environment. Case closed. But that would become another false ending, because a far more mysterious clue was waiting just beyond the boundary. A clue carried by particles travelling at extraordinary speeds. Particles that did not originate within the solar system. Particles that had crossed vast regions of the galaxy before reaching Voyager. Particles carrying messages from distant and violent events. Cosmic rays. And what they revealed would change the story once again. By the middle of the 2010s, many scientists felt a sense of cautious satisfaction, not certainty. Science rarely offers certainty, but satisfaction. The major pieces of the puzzle appeared to fit together. Voyager had crossed the heliopause. The spacecraft was measuring interstellar plasma. The surrounding environment was likely shaped by ancient supernovae. The mysterious magnetic behavior could be explained through interactions between the heliosphere and the local interstellar medium. The story was becoming coherent. Complex, certainly, but coherent. For the public, the mystery seemed largely solved. Humanity had reached interstellar space. Mission accomplished. The spacecraft continued its journey. Researchers continued collecting data. The headlines faded once more. And that is often when science becomes most interesting. Because reality has a habit of waiting until everyone relaxes before revealing the next complication. The first signs appeared quietly. No dramatic announcement. No single revolutionary discovery. Just an accumulation of small inconsistencies. Measurements that refused to fit perfectly. Patterns that seemed slightly off. Tiny cracks in an increasingly comfortable narrative. At first, few people paid much attention. After all, anomalies are common. Spacecraft instruments age. Environmental conditions fluctuate. Unexpected readings occur. Most disappear with further analysis. These did not. Instead, the anomalies began reinforcing one another. The more carefully scientists examined Voyager's observations, the more they realized something unsettling. The interstellar medium surrounding the solar system might be far more structured than previously believed. This was an important distinction. Earlier models often treated the local interstellar environment as relatively smooth, not perfectly uniform, but reasonably predictable. Voyager suggested something else. The spacecraft appeared to be moving through an environment containing subtle variations, changes in density, changes in pressure, changes in magnetic behavior. The darkness between stars seemed layered, textured, almost geological. The analogy was striking. Imagine flying over Earth at night. From a distance, the planet appears smooth, uniform, simple. As you descend, complexity emerges. Mountains, rivers, cities, forests. The closer you look, the richer the landscape becomes. Voyager was producing a similar effect. Interstellar space appeared increasingly detailed, increasingly complicated. And that complexity created a new question. If the local interstellar medium possessed structure, what created it? The obvious answer involved ancient supernovae. Researchers had already linked the local bubble to stellar explosions. Shockwaves could compress matter, shape magnetic fields, generate large-scale features. The explanation seemed plausible, yet there was a problem. Some observed structures appeared surprisingly organized, more organized than expected. The galaxy, at these scales, looked less like random turbulence and more like an engineered system, not engineered in the literal sense, but ordered, coherent, as though invisible rules governed the arrangement. Scientists began focusing more intensely on magnetic fields, again. Every path seemed to lead back to magnetism. The deeper researchers investigated, the more they realized that magnetic fields might be doing far more than previously appreciated. They were not merely influencing interstellar space, they were shaping it. This represented a profound shift in perspective. Imagine studying a city for decades while assuming roads are secondary details, then suddenly realizing the roads determine almost everything: traffic, growth, economics, communication. The roads were not background features, they were the framework. Researchers increasingly suspected that magnetic fields played a similar role throughout the interstellar medium, invisible frameworks organizing matter across enormous distances. The idea explained many observations, perhaps the density puzzle, perhaps certain cosmic ray patterns, perhaps even aspects of the heliosphere itself. For a moment, the mystery seemed to be converging again. The pieces fit. Once more, reality refused to cooperate. Because the cosmic rays themselves were becoming difficult to ignore, Voyager's instruments were recording particles unlike anything routinely encountered near Earth. These particles arrived from deep space, from beyond the heliosphere. Some possessed astonishing energies. Others carried clues about conditions far from the solar system. Collectively, they represented something extraordinary. Direct samples of the galaxy, not photographs. Not telescopic observations, actual particles arriving from distant environments. The implications were enormous. Cosmic rays effectively transformed Voyager into a galactic observatory. The spacecraft was no longer merely studying local conditions, it was intercepting messengers from elsewhere in the Milky Way. And those messengers carried surprises. Researchers expected certain cosmic ray intensities after Voyager crossed the heliopause. The observations partly matched expectations, partly not entirely. Some particle populations behaved differently than predicted. Some energy distributions appeared unusual. Certain variations occurred over time. The environment seemed more dynamic than expected. This was troubling. Interstellar space had often been imagined as relatively stable. Changes occur, certainly, but generally over immense timescales. Voyager hinted at something more active, more responsive, more alive. The realization created a larger question. How much of what Voyager observed reflected local conditions, and how much reflected processes occurring across the galaxy? The distinction mattered. If the measurements were local, the mystery remained relatively contained. If they reflected galactic-scale phenomena, the implications expanded dramatically. The investigation would no longer concern merely the solar system's boundary. It would concern the behavior of the Milky Way itself. Scientists began looking outward, far outward, toward the origins of cosmic rays, toward the processes generating them, toward the ancient stellar explosions suspected of accelerating them. The scale escalation was immense. The mystery had grown from a spacecraft leaving the solar system to a question about the energetic history of an entire galaxy, and that growth revealed something fascinating. Voyager was no longer investigating a boundary, it was investigating connections. Connections between stars, connections between supernovae, connections between magnetic fields and particles, connections linking distant events across unimaginable distances. The darkness between stars was beginning to resemble a network, an interconnected environment rather than an empty gap, a place where information travelled, a place where history accumulated, a place where the past remained visible long after its original sources vanished. For a moment, scientists believed they understood the nature of that network. Then Voyager encountered evidence suggesting that some of the particles surrounding it had travelled through space for millions of years, perhaps longer. And those ancient travellers carried clues from stellar catastrophes so distant in time that they occurred before humanity existed. The investigation was about to become much larger, because the next mystery would not concern where Voyager was. It would concern where the particles around Voyager had come from, and some of those journeys began in stars that died long before Earth looked anything like the world we know today. The particles surrounding Voyager were invisible. No camera could capture them. No human eye could see them. Yet they were among the most important clues in the entire investigation, because while stars shine light across the galaxy, cosmic rays carry something different. History. Fragments of ancient events, evidence from places that may no longer exist in the form they once did. And as Voyager moved beyond the heliosphere, those ancient messengers arrived in unprecedented numbers. At first glance, cosmic rays sound almost insignificant. The term suggests something small, perhaps even harmless. In reality, many are among the most energetic particles known. Some travel at speeds approaching the speed of light. Some possess energies so extreme that they challenge our understanding of how nature accelerates matter. They are tiny, yet astonishingly powerful, and they come from somewhere. That simple fact transformed them into clues. Every cosmic ray detected by Voyager had a story, a point of origin, a journey, a history. The challenge was reconstructing it. Imagine finding a message in a bottle washed onto a beach. The bottle itself matters, but the greater mystery concerns where it came from, who sent it, how far did it travel, what oceans did it cross. Cosmic rays posed similar questions. Each particle arriving at Voyager represented a traveller. Some had crossed immense portions of the Milky Way. Others may have spent millions of years wandering through interstellar space. And unlike Earthbound investigators, scientists could not simply retrace their paths. The particles carried clues, not maps. Researchers therefore approached the problem indirectly. They examined energies, compositions, arrival rates, patterns hidden within the data. Gradually, certain conclusions emerged. Many cosmic rays appear to originate in supernova remnants. This made intuitive sense. Supernovae release enormous amounts of energy. Shock waves expand outward. Magnetic fields become tangled and compressed. These conditions can accelerate particles to extraordinary speeds. The process resembles a cosmic slingshot. A particle crosses a shock front, gains energy, crosses again, gains more. Over time, the energy accumulates. Eventually, particles escape into the galaxy. Once released, they begin journeys spanning distances difficult to comprehend. A single particle may wander through interstellar space for millions of years before encountering a detector. The idea is extraordinary. Imagine receiving a letter written before human civilization began, a message that spent millions of years in transit. That is effectively what Voyager was intercepting, ancient messengers from ancient events. And the farther the spacecraft travelled beyond the heliosphere, the clearer those messages became. This revealed something important about the solar system itself. The heliosphere is not merely a boundary, it is a filter, a shield, a protective cocoon that blocks many incoming cosmic rays. While Earth remains inside that cocoon, we experience only part of the galactic environment. Voyager had moved beyond it. The spacecraft was now observing conditions much closer to their true interstellar state. The difference was dramatic. Cosmic ray intensities rose sharply. The galaxy became louder. Not louder in sound, louder in particles. Imagine spending your entire life inside a quiet building, then stepping outdoors during a storm. The environment suddenly feels more active, more energetic, more alive. That was essentially what happened when Voyager crossed the heliopause. The spacecraft entered a realm where galactic influences became far more apparent. For scientists, the implications were profound. The solar system was not isolated. It was immersed within a larger environment, continuously interacting with it. A flow of particles connected our neighborhood to distant regions of the galaxy, and those connections raised uncomfortable questions. How stable was the heliosphere? How effectively did it shield Earth? Had cosmic ray levels changed throughout Earth's history? Could future changes affect life? These questions transformed cosmic rays from an astrophysical curiosity into something much more personal. The particles arriving at Voyager were not merely evidence of distant events. They were part of the environment surrounding humanity itself. The investigation was becoming increasingly intimate. Then another puzzle emerged. Not all cosmic rays behaved the same way. Some energies appeared more abundant than expected. Others appeared suppressed. Certain variations fluctuated over time. The patterns hinted at invisible influences again. Researchers increasingly suspected that magnetic fields were responsible. The particles did not travel through empty space. They travelled through a complex network of magnetic structures. Imagine releasing a drop of dye into a river system. The final path depends not only on the water itself, but on channels, currents, bends, and obstacles. Cosmic rays appeared to experience something similar. Their journeys were shaped by an invisible galactic infrastructure, a hidden architecture extending across enormous distances. The realization carried remarkable implications, because if magnetic fields guide cosmic rays, then those particles effectively map the structure of the galaxy. Not directly, indirectly, like leaves revealing the shape of a stream. The particles exposed pathways otherwise impossible to observe, and those pathways hinted at a deeper level of organization. The Milky Way was beginning to resemble a living network, not conscious, not biological, but interconnected, dynamic, a system in which distant events influenced distant regions through flows of energy and matter. Voyager's observations repeatedly pointed toward this conclusion. The darkness between stars was not passive. It participated, it transported, it connected. Then, scientists noticed something even stranger. Certain cosmic rays appeared extraordinarily old, not merely thousands of years old, not even hundreds of thousands, millions, perhaps tens of millions. The particles had spent unimaginable lengths of time wandering through the galaxy, long enough for entire ecosystems on Earth to evolve, long enough for continents to shift, long enough for species to appear and vanish. The realization was difficult to grasp. Some of the particles striking Voyager might have begun their journeys before our earliest human ancestors existed, before the modern shape of Earth emerged, before the world itself looked familiar. These particles were relics, travelling fossils, physical survivors from forgotten chapters of galactic history. And if that was true, another mystery immediately followed. How could such particles survive so long? What paths had they followed? What hidden structures allowed them to persist across such vast spans of time? The answers seemed connected to the same invisible architecture appearing throughout the investigation. Magnetic fields, interstellar networks, ancient scars left by supernovae. The clues were converging. Yet the convergence revealed a larger mystery rather than a solution. Because if Voyager was intercepting particles from ancient stellar catastrophes, then the spacecraft was not merely studying the present, it was reading a historical record written across the galaxy itself. And the next clues suggested that some of those records originated from stars that died long before humanity ever looked toward the sky. Every civilization leaves traces behind: ruins, artifacts, records, fragments that survive long after the original builders are gone. Astronomers eventually realize that stars do something remarkably similar. A star can die, its light can fade, its planetary system can change beyond recognition, yet evidence of its existence may continue travelling through the galaxy for millions of years. Voyager was beginning to intercept that evidence, not through photographs, not through telescopes, but through particles, tiny messengers carrying information from ancient stellar catastrophes. And the implications were astonishing, because some of the particles reaching Voyager may have begun their journeys long before humanity existed, long before civilization, long before the first human ancestor ever stood upright beneath the African sky. The realization required a different way of thinking about time. Human history spans thousands of years. Recorded history spans only a fraction of that. Even the oldest monuments on Earth are young by galactic standards. The particles surrounding Voyager belong to a much older story. A story measured not in centuries, but in millions of years. Imagine receiving a letter written during the age of dinosaurs. Now imagine receiving one written before the dinosaurs. That begins to approach the timescales involved. Cosmic rays are not ordinary travellers. Their journeys are often extraordinarily long. Unlike light, which generally follows relatively direct paths through space, charged particles interact with magnetic fields. They bend, scatter, wander. Their roots become tangled. A particle may travel an immense total distance while making relatively little overall progress toward its destination. The analogy is simple. Imagine trying to cross a continent while being repeatedly redirected by winding roads. You eventually arrive, but the journey takes far longer than a straight-line path. Cosmic rays experience something similar. Magnetic fields turn the galaxy into a maze. Particles spend vast amounts of time wandering through it. This creates an extraordinary possibility. The particles Voyager detects today may preserve information about events that occurred millions of years ago. The spacecraft is not merely observing present conditions, it is sampling ancient history. Researchers began treating cosmic rays almost like archaeological artifacts, not because they remained unchanged, but because they carried clues about environments that no longer exist in their original form. Certain elements proved especially valuable. The composition of cosmic rays reveals information about the stars that produced. Some contain traces of processes occurring deep inside massive stars. Others reflect the conditions present during supernova explosions. Each particle population becomes a piece of evidence, a fragment of a larger story. And that story kept pointing towards stellar death, again and again. Throughout the Milky Way, stars live and die continuously. Massive stars explode. Shockwaves spread outward. Matter is recycled into new generations of stars. The galaxy is not static. It is constantly rebuilding itself, a vast cosmic ecosystem. Voyager's observations offered direct evidence of that process. The particles surrounding the spacecraft were reminders that the Milky Way is a place of ongoing transformation, a place where destruction creates opportunity, where endings become beginnings, where dead stars contribute to future worlds. The idea was beautiful and unsettling because it implied that everything familiar ultimately originates from forgotten catastrophes. The calcium in bones, the iron in blood, the oxygen in every breath. Many of the elements essential to life were forged inside stars that died long before the solar system formed. Humanity itself is connected to stellar history. Voyager was simply revealing those connections more clearly. The spacecraft had become a witness to a hidden continuity linking past and present, a continuity stretching across unimaginable spans of space and time. Then another question emerged, a troubling one. If cosmic rays preserve information about ancient events, how complete is the record? What might be missing? This question haunted researchers because interstellar space is not a perfect archive. Particles are lost, paths become scrambled, signals fade. Much of the galaxy's history may have vanished forever. Voyager's observations represented only fragments, scattered remnants, surviving traces. The situation resembled reconstructing an ancient civilization from a handful of broken artifacts. Useful information exists. Important information exists. Yet enormous gaps remain. The darkness between stars preserves history imperfectly, and that imperfection introduces uncertainty. Scientists could infer origins, estimate timescales, propose explanations, but complete certainty remained elusive. The mystery endured. In fact, it grew. Because the more researchers studied cosmic rays, the more they realized the particles were telling two stories simultaneously. One story concerned their origins, supernovae, massive stars, ancient explosions. The other concerned their journeys, and those journeys proved equally fascinating. To survive for millions of years, particles require pathways, routes, mechanisms that prevent them from simply escaping the galaxy altogether. Something was influencing their motion. Something was shaping their distribution. Again, the evidence pointed toward magnetic fields, the same invisible structures appearing throughout Voyager's observations. Researchers increasingly viewed the Milky Way as a web of magnetic connections, not a perfect web, not a simple one, but a network nonetheless. The galaxy possessed hidden infrastructure, invisible channels through which particles moved, invisible frameworks organizing matter and energy. The concept transformed how scientists thought about interstellar space. The darkness was no longer merely a location, it was a system, a dynamic environment connecting distant events across enormous scales. Ancient supernovae influenced modern observations. Distant stellar deaths affected local particle populations. Everything appeared linked. The scale of the mystery continued expanding. What began as a question about the solar system's edge was becoming a question about the structure of the galaxy itself. And with each expansion came a new realization. Voyager's discoveries were revealing not only what existed between stars, they were revealing how interconnected the universe truly is. For a moment, this seemed to provide a satisfying answer. Ancient stars produced the particles. Magnetic fields guided them. The galaxy connected everything together. The mystery appeared increasingly coherent. Then, another complication emerged, one that threatened to alter the picture yet again. Because the heliosphere itself, the immense bubble surrounding the solar system, began to look far stranger than anyone had imagined. Its shape, its size, even its basic structure became subjects of renewed debate, and understanding that structure would prove essential. Because before humanity could fully understand the darkness between the stars, it first needed to understand the strange bubble drifting through that darkness. The bubble we call home. For decades, artists drew it the same way. Textbooks showed it the same way. Scientific illustrations repeated the same basic image. The solar system traveled through the galaxy like a comet, a rounded front, a long, trailing tail. The giant bubble stretched backward by its motion through interstellar space. The picture seemed reasonable. After all, we see similar shapes throughout nature. A boat moving through water creates a wake. A meteor creates a trail. A comet grows a tail as solar radiation pushes material away. Why should the heliosphere be different? The image became familiar, comforting, almost intuitive. There was only one problem. Voyager's observations increasingly suggested that reality might not look anything like the picture, and if the shape was wrong, many other assumptions might be wrong as well. The issue emerged gradually. No single measurement revealed the truth. Instead, researchers found themselves confronting a growing collection of inconsistencies. Particle distributions, magnetic field orientations, pressure measurements, cosmic ray behavior. Each observation provided only a partial clue, but together they pointed towards an uncomfortable possibility. The heliosphere might be far more complex than anyone imagined. To appreciate why this mattered, it helps to understand what the heliosphere actually is. At its simplest, the heliosphere is a bubble created by the sun. The solar wind streams outward in every direction. For billions of miles, it dominates the surrounding environment. Eventually, however, it encounters resistance from interstellar space. The outward pressure balances against the inward pressure. A boundary emerges. The result is a vast protective cocoon surrounding the solar system. Everything humanity has ever known exists inside it. Every planet, every moon, every spacecraft except the Voyagers, every human who has ever lived. All of it resides within this invisible structure, and yet until recently, nobody knew its true shape. Imagine discovering that no one has ever accurately mapped the continent on which civilization exists. That was essentially the situation. The heliosphere is enormous, far too large to observe directly from a distance. Scientists must reconstruct its shape indirectly, through models, measurements, and clues. Voyager provided some of the most important clues ever obtained. The problem was that the clues disagreed with expectations. Some models predicted a long tail extending thousands of astronomical units behind the solar system. Others suggested a shorter structure. Some proposed a comet shape. Others envisioned something more spherical. Then a radically different possibility appeared, a heliosphere resembling a croissant. The idea initially sounded almost absurd, a cosmic pastry drifting through space. Yet the underlying science was serious. Certain simulations indicated that the sun's magnetic field might constrain the heliosphere in unexpected ways. Instead of producing a long, narrow tail, magnetic forces could shape the bubble into twin lobes. The resulting structure would look dramatically different from traditional illustrations. Researchers debated intensely. Was the heliosphere comet-like, croissant-like, something else entirely? The disagreement reflected a deeper problem. No one possessed enough direct observations. Humanity was attempting to reconstruct an immense structure from a handful of measurements. The challenge resembled trying to map an entire ocean using data from two drifting buoys. Voyager 1 provided one perspective. Voyager 2 provided another. Both were invaluable. Neither was sufficient on its own. Yet the observations revealed something important. The heliosphere was not symmetrical, not simple, not static. The bubble appeared shaped by forces operating across enormous scales. The sun influenced it. Interstellar pressure influenced it. Magnetic fields influenced it. Perhaps ancient supernovae influenced it as well. Everything was connected, again. That theme kept returning. The deeper scientists investigated, the more interconnected the story became. Then Voyager 2 added another complication. When it crossed the heliopause in 2018, the details differed from Voyager 1's experience. Not dramatically, but significantly. The boundary appeared at a different distance. Certain particle behaviors varied. The environment was not identical. This surprised researchers. If the heliosphere were perfectly uniform, such differences would be difficult to explain. Instead, the observations suggested a distorted structure, an uneven frontier. The solar system's protective bubble resembled a weather system more than a geometric object. Imagine a balloon floating through turbulent winds. The surface flexes, pressure changes, different regions experience different conditions. The heliosphere increasingly appeared to behave in a similar way. This realization carried important implications. Because the heliosphere acts as Earth's first line of defense against cosmic radiation, its shape influences how effectively that protection operates. A stronger region blocks more particles. A weaker region allows more through. Understanding the heliosphere, therefore, means understanding part of the environment that makes life on Earth possible. The mystery was becoming personal again. The shape of the heliosphere was not merely an abstract scientific question. It affected the relationship between humanity and the galaxy around it. And that relationship was proving more dynamic than expected. Then researchers noticed something particularly intriguing. The heliosphere appeared surprisingly sensitive to conditions beyond itself. Changes in the local interstellar medium influenced its behavior. External pressures influenced its boundaries. Magnetic fields beyond the solar system shaped its structure. The implication was profound. The solar system was not isolated. It responded continuously to its galactic surroundings, like a ship responding to ocean currents, like a living cell responding to its environment. The heliosphere interacted with the galaxy constantly. Voyager was revealing that interaction in unprecedented detail. For a moment, it seemed the investigation had reached a satisfying stage. The boundary was complex. The shape was dynamic. The interactions were interconnected. The mystery appeared larger than expected, but understandable. Then another realization emerged, a disturbing one. Researchers had spent years studying the heliosphere itself, but perhaps they were focusing on the wrong scale. Perhaps the true mystery did not concern the solar system's bubble at all. Perhaps the real mystery concerned the medium surrounding it, the vast environment through which the heliosphere travelled, the local interstellar medium, the local bubble, the ancient scars of supernovae, the invisible magnetic architecture of the Milky Way. In other words, perhaps Voyager's greatest discovery was not about the edge of the solar system. Perhaps it was about the darkness beyond. And the more scientists examined that darkness, the less empty it appeared. The void between stars was beginning to reveal itself as an active environment, a place with structure, a place with history, a place with hidden rivers of energy and matter flowing across enormous distances. The heliosphere was merely the shoreline. The true ocean lay beyond. And in the next phase of the investigation, that ocean would begin revealing its secrets. There is a moment in many investigations when the evidence stops pointing toward isolated clues and begins revealing an entire hidden world. The scattered fragments suddenly connect. The individual mysteries become part of a larger pattern. The detective realizes the case was never about a single event. It was about an entire system operating behind the scenes. Voyager's journey had reached that moment. For years, scientists treated the space between stars as a backdrop, a setting, a stage upon which more interesting objects existed. Stars mattered. Planets mattered. Galaxies mattered. Interstellar space was merely the emptiness separating them. Voyager was dismantling that assumption, piece by piece. The darkness was not empty. It was not passive. And it was certainly not silent. Instead, it appeared to be an environment with its own dynamics, its own history, and its own hidden structures. The realization changed everything, because once interstellar space becomes an environment, new questions immediately emerge. How does it evolve? How does it transport energy? How does it influence stars, planets, and entire solar systems? The investigation was no longer about crossing a boundary. It was about understanding an ecosystem, a galactic ecosystem. The evidence supporting this shift came from multiple directions. Plasma measurements revealed density, cosmic rays revealed connectivity, magnetic fields revealed organization, ancient supernova remnants revealed history. Separately, each clue was interesting. Together, they told a story in which the darkness between stars acted less like a vacuum and more like an ocean. An extraordinarily thin ocean, certainly, yet an ocean nonetheless. Imagine looking across Earth's seas from orbit. At first glance, the water appears smooth, featureless, uniform. But closer examination reveals currents, temperature gradients, eddies, storm systems, regions of biological activity. Hidden complexity emerges. Voyager suggested the same thing was true on a galactic scale. The apparent emptiness between stars concealed an intricate environment, shaped by countless interacting processes. And like any ocean, it possessed circulation. The exact mechanisms differed from earthly water currents, but the principle remained familiar. Matter moved. Energy moved. Magnetic influences propagated. Particles travelled. The galaxy was not composed of isolated islands of stars. It was connected by flows, invisible flows. This realization helped explain many of Voyager's most puzzling observations. Why did cosmic rays arrive from distant regions? Because pathways existed. Why did particle populations vary? Because conditions varied. Why did magnetic fields appear so important? Because they helped organize the entire system. The darkness was not random. It was structured. The implications were enormous. For centuries, astronomers focused primarily on luminous objects. Stars and galaxies naturally attract attention because they can be seen. Interstellar space cannot. Voyager was revealing a hidden layer of reality that had largely escaped direct observation, a layer that might be just as important as the visible one. Then, another perspective shift occurred. Researchers began comparing the interstellar medium to Earth's atmosphere. The analogy was imperfect, yet surprisingly useful. Humans rarely think about the atmosphere. We live inside it continuously. It feels ordinary, invisible, easy to ignore. Yet the atmosphere controls weather, climate, temperature, and life itself. Its influence is profound despite its apparent invisibility. Interstellar space may play a similar role on galactic scales. Stars exist within it. Solar systems move through it. Magnetic fields shape it. Cosmic rays travel through it. The medium influences everything around it. Yet for most of scientific history, it remained largely hidden. Voyager was making the invisible visible, and the deeper researchers looked, the more evidence they found for complexity. Density variations appeared significant. Magnetic structures appeared widespread. Ancient stellar explosions left long-lasting effects. The galaxy seemed to possess memory, not conscious memory, physical memory. Events from millions of years ago continued influencing present conditions. The local bubble itself represented a perfect example. Long-dead stars still shaped the environment surrounding the solar system. Ancient catastrophes remained visible in the structure of interstellar space. History lingered. That persistence fascinated scientists because it suggested that interstellar space preserves information. Not perfectly, not indefinitely, but long enough for traces to survive. The darkness acts like an archive, a vast and incomplete archive, yet an archive nonetheless. And archives invite questions. What other histories remain preserved? What forgotten events left traces still drifting through the galaxy? What stories are hidden in the structure surrounding Voyager? The possibilities seemed endless. Then researchers confronted another striking implication. If interstellar space influences solar systems, then the solar system's environment has likely changed throughout its history. The Sun does not remain fixed. It moves through the Milky Way. Over millions of years, it encounters different regions, different densities, different magnetic conditions, different cosmic ray environments. Earth's cosmic neighborhood is not permanent. It evolves. Imagine a ship sailing through changing seas. Sometimes the waters are calm, sometimes turbulent, sometimes warm, sometimes cold. The ship changes little. The environment changes constantly. The solar system may experience something similar. Voyager's observations hinted that our current location represents only one chapter in a much longer journey, a journey through diverse regions of the galaxy. The realization expanded the mystery yet again. Now the question was not simply what interstellar space is. The question became how interstellar space changes, and how those changes affect worlds like Earth. The stakes continued growing. What began as a story about a spacecraft had become a story about humanity's place within a dynamic galaxy. For a moment, scientists felt they had finally uncovered the central truth. The darkness between stars was not empty. That was the revelation. That was the answer. But answers have a habit of generating new questions. And this answer generated one of the largest yet. Because if the interstellar medium is structured, organized and interconnected, then what creates that organization? What hidden framework gives shape to the darkness? Again and again, the evidence pointed toward the same suspect. Magnetic fields. Invisible. Difficult to observe, yet apparently fundamental. The investigation was about to descend into an even deeper layer of reality. A hidden network stretching across interstellar distances, a network Voyager could only glimpse indirectly. But those glimpses suggested something remarkable. The galaxy might contain invisible rivers flowing beneath the darkness itself, and understanding those rivers would transform the mystery once again. Ancient civilizations often built themselves around rivers. The Nile, the Tigris, the Euphrates, the Yangtze. The rivers could not always be seen from a distance, but their influence was unmistakable. They guided movement, transported resources, connected distant regions, shaped entire histories. Scientists increasingly suspected that the Milky Way possessed something similar. Not rivers of water, rivers of influence, invisible channels running through interstellar space. And Voyager's observations were providing some of the first direct clues that such structures might exist. The idea emerged from a frustrating pattern. Again and again, researchers found evidence that particles did not move randomly through the galaxy. Cosmic rays appeared guided, organized. Their distributions contained structure. Their journeys displayed patterns. The behavior suggested hidden pathways. At first, scientists were cautious. Patterns can be deceptive. Humans are remarkably good at seeing order, even where none exists. Extraordinary claims require extraordinary evidence. Yet the clues kept accumulating. Magnetic field measurements, particle transport models, observations from other spacecraft, astronomical surveys of distant regions. The evidence pointed in the same direction. The galaxy appeared threaded with magnetic structures, and those structures influenced everything. To understand why, imagine releasing a leaf into a river. The leaf does not choose its path. The current chooses for it. The shape of the river determines where it travels. Cosmic rays may experience something similar. They possess energy. They possess motion. Yet magnetic fields help determine their routes. The particles are travelers. The magnetic fields are roads. Invisible roads. And the galaxy contains far more of them than anyone once imagined. This realization represented a major shift in perspective. For much of the 20th century, magnetic fields occupied a somewhat secondary role in astronomy. Important, certainly, but often treated as supporting actors. Voyager's discoveries helped elevate them to something much larger. Perhaps magnetic fields were not merely influencing the galaxy. Perhaps they were helping organize it. The possibility was profound, because magnetic fields exist almost everywhere. Around planets, around stars, within nebulae, across galaxies, even between galaxies. They are among the most widespread structures in the universe, yet they remain difficult to see directly. Astronomers usually infer their presence through effects: the bending of particles, the polarization of light, the motion of plasma. Like wind moving through trees, the field itself remains invisible, while its influence becomes apparent. Voyager was observing those influences firsthand. The spacecraft repeatedly detected evidence that particles were responding to unseen magnetic architecture, and the deeper scientists investigated, the larger that architecture appeared. At first, researchers focused on local structures, the immediate environment surrounding the solar system, the local bubble, nearby interstellar clouds, reasonable scales, manageable scales. Then the evidence began pointing outward, farther outward. Magnetic patterns appeared connected across enormous distances. The implication was startling. The Milky Way might contain magnetic networks extending for thousands of light years, perhaps tens of thousands. Structures so vast that entire civilizations could never traverse them within a human lifetime. Yet these invisible frameworks quietly shaped the movement of matter and energy throughout the galaxy. The scale escalation was breathtaking. Once again, the mystery grew. What began as a question about Voyager's surroundings was becoming a question about the hidden infrastructure of the Milky Way. Researchers started comparing the situation to Earth's transportation systems. Roads connect cities, railways connect regions, shipping lanes connect continents. Remove those networks and civilization changes fundamentally. The galaxy may possess equivalent systems, not built intentionally, not engineered. Yet, equally important, magnetic structures create preferred routes, preferred flows, preferred patterns of movement. Cosmic rays follow them. Charged particles follow them. Energy follows them. The darkness between stars becomes interconnected, not through physical tunnels, through invisible fields. This helped explain something that had puzzled astronomers for decades. Certain cosmic ray populations seemed surprisingly well mixed across large portions of the galaxy. Others appeared confined. Some regions behaved like open highways, others behaved like barriers. The patterns made more sense once magnetic architecture entered the picture. The galaxy was not uniform. It contained pathways, and pathways create behavior. The analogy becomes clear if you imagine rain falling across a landscape. The water lands everywhere, yet rivers form in specific locations. The terrain guides the flow. Similarly, cosmic rays may originate throughout the galaxy, but magnetic fields guide where they travel. Voyager was revealing traces of that process. Then another fascinating implication emerged. If magnetic structures persist long enough, they could preserve information about ancient events. Again, the theme of memory appeared. Ancient supernovae might leave lasting signatures. Past stellar activity might influence present conditions. History could remain embedded within the architecture itself. The darkness between stars was beginning to resemble an archive and a transportation network simultaneously. A place where information survived. A place where information moved. The combination was remarkable and unsettling because it suggested the galaxy might be far more interconnected than previously believed. A supernova occurring hundreds of light years away could eventually influence regions far beyond its original location. Not instantly, not dramatically, but gradually. Through particles, through magnetic structures, through long chains of cause and effect. Everything appeared linked. The farther Voyager travelled, the stronger this impression became. The spacecraft was not discovering isolated phenomena. It was uncovering relationships, connections hidden beneath the apparent emptiness of space. For a moment, this seemed like the answer researchers had been seeking. The darkness contained structure. Magnetic fields provided organization. Ancient supernovae supplied history. Cosmic rays carried information. The pieces fit together beautifully, perhaps too beautifully. Because nature rarely rewards investigators with perfectly tidy conclusions. And soon another complication appeared, one that forced scientists to revisit assumptions about the solar system's neighborhood yet again. The local bubble. The ancient cavity surrounding our star. For years it seemed to provide a satisfying explanation, a scar left by long dead stars, a historical remnant preserved in interstellar space. Case closed. Except the newest evidence suggested the local bubble might be far more complex than a simple scar. It might still be evolving, still interacting, still shaping the environment around Voyager. And if that was true, then the investigation was far from over. The answer had created a bigger question once again. Every neighborhood has a past. The houses may be new. The roads may appear modern. The people may know little about what came before. Yet beneath the surface, older stories remain buried. Forgotten settlements, abandoned foundations, lost generations whose actions still shape the present. Astronomers were beginning to realize that the solar system's neighborhood possessed a similar history, and Voyager had become one of the most important witnesses. For decades, the local bubble appeared relatively straightforward, an enormous cavity, a region of low-density interstellar space surrounding the Sun. Most researchers agreed that ancient supernovae probably created it. The explanation fit the evidence. Powerful explosions could excavate large volumes of gas. Shockwaves could shape surrounding material. The story made sense. But as observations improved, the story became more complicated. The local bubble no longer looked like a single scar. It began to resemble the aftermath of an entire sequence of events, a chain reaction stretching across millions of years. The distinction mattered. A single explosion leaves one kind of remnant. Multiple generations of explosions leave something far more complex. Imagine walking through a forest that burned once. Then imagine walking through a landscape shaped by repeated fires over centuries. The terrain would tell different stories. The same principle applies to interstellar space. Researchers increasingly suspected that numerous stellar deaths contributed to the environment surrounding the solar system. Not one catastrophe, many, and each left traces behind. The evidence came from multiple sources. Astronomical surveys mapped nearby interstellar clouds. Computer simulations reconstructed ancient stellar motions. Observations of radioactive isotopes provided additional clues. Piece by piece, investigators began reconstructing a forgotten chapter of galactic history. The picture that emerged was remarkable. Millions of years ago, groups of massive stars may have occupied regions relatively close to our current location. These stars lived brief, brilliant lives. Then they exploded, one after another. Their shock waves expanded through surrounding space. Gas was compressed. Magnetic fields were reshaped. Entire regions were transformed. Over time, a vast cavity emerged, the local bubble. But the story did not end there, because the shock waves themselves continued interacting, colliding, overlapping, generating new structures. The resulting environment became extraordinarily complex. The darkness surrounding the solar system was not simply empty space. It was the product of accumulated history, layer upon layer of history. The analogy is geological. A mountain cliff reveals different layers of rock. Each layer records a different era, different conditions, different events. The local bubble may preserve something similar on a galactic scale, a stratified record of ancient stellar activity. Voyager was traveling through the outermost portions of that record, and the deeper scientists investigated, the more interconnected everything appeared. Nearby interstellar clouds seemed related to past supernova activity. Magnetic structures appeared linked to ancient shockwaves. Particle populations carried evidence of long-forgotten events. Nothing existed in isolation. Every clue pointed toward a history richer than anyone had anticipated. Then researchers made an intriguing realization. The solar system itself is not a passive observer. It moves continuously. As the Sun orbits the Milky Way, it travels through different environments, different regions of interstellar space, different chapters of galactic history. The local bubble is simply the current chapter. Eventually, another will follow. This transformed the mystery in an important way. Voyager was not merely revealing what exists around the solar system today. It was revealing a temporary condition, a snapshot, one moment in a much longer journey. Imagine a ship crossing an ocean. At any given moment, the crew experiences a particular region, particular weather, particular currents, yet the voyage continues. Conditions change, new environments appear. The solar system may experience something similar over millions of years. Our current neighborhood is not permanent. The realization carried profound implications. Earth's galactic environment has changed before. It will change again. And those changes may influence cosmic ray exposure, interstellar pressure, magnetic conditions, perhaps even planetary environments. The galaxy is not merely scenery. It participates. It interacts. It shapes the conditions under which worlds exist. Voyager's observations repeatedly reinforce this conclusion. The darkness between stars was active, dynamic, historically rich. Then, another question emerged, one that troubled researchers. If the local bubble resulted from multiple supernovae, where exactly are the boundaries? The answer proved surprisingly difficult. The cavity did not possess sharp walls. Instead, its edges appeared complex, irregular, shaped by countless interactions. Some regions contained denser clouds, others appeared more diffuse. The boundaries themselves carried history. This complexity challenged earlier assumptions. Scientists increasingly realized that categories such as inside and outside were often oversimplifications. Nature prefers gradients, transitions, overlapping structures. The local bubble was no exception, and that realization echoed one of Voyager's earliest lessons. The heliopause was not a simple wall. The local bubble was not a simple cavity. The universe rarely organizes itself into neat compartments. Instead, structures overlap, influences interact, histories intertwine. The deeper researchers looked, the more obvious this became. For a moment, it seemed the local bubble finally explained everything. The density puzzle, the supernova evidence, the cosmic ray environment, the magnetic structures. A satisfying picture emerged. Then new observations complicated the story again, because evidence suggested that the local bubble might still be interacting with neighboring structures, nearby interstellar clouds, adjacent cavities, larger galactic environments. The scar was not isolated. It was connected, just as rivers connect landscapes. Magnetic structures and shockwave remnants appeared to connect different regions of interstellar space. The scale of the investigation expanded once more. The local bubble was no longer merely a local phenomenon. It was part of something larger, a network of structures extending across significant portions of the Milky Way. And that realization created another false ending. Scientists thought they had reconstructed the history of our neighborhood. Instead, they had uncovered evidence that the neighborhood itself belonged to a much larger system, a system Voyager could only glimpse. Yet those glimpses hinted at a galaxy far more interconnected than anyone once believed. The mystery was growing again, and the next discovery would force researchers to reconsider whether the local interstellar medium was truly understood at all. By now, the investigation seemed to possess all the essential pieces. The heliosphere explained the solar system's protective bubble. The local bubble explained the unusual environment surrounding it. Ancient supernovae explained the scar-like structure of our galactic neighborhood. Magnetic fields explained the organization of particles moving through interstellar space. Cosmic rays carried messages from long-dead stars. Everything appeared connected. Everything appeared coherent. For many researchers, this felt like the moment when the mystery finally settled into focus. Not completely solved. Science rarely works that way, but understood. The broad outline seemed clear. Voyager had crossed into interstellar space and revealed a hidden environment shaped by ancient stellar history. It was a satisfying narrative, elegant even, which is precisely why scientists became suspicious. Nature has a habit of resisting elegant conclusions, and the more carefully researchers examined the evidence, the more they noticed something troubling. The local interstellar medium still refused to behave like a simple environment. Small inconsistencies remained. Minor anomalies persisted. Tiny deviations appeared in models. Individually, none seemed particularly important. Together, they hinted that the story was incomplete. The first clue came from scale. For years, astronomers tended to think of the local bubble as a relatively self-contained structure, a cavity created by ancient supernovae, a distinct feature, a specific region of space. Reasonable assumptions. Yet newer observations suggested the boundaries were less isolated than expected. The local bubble appeared connected to neighboring structures, connected to adjacent cavities, connected to larger regions of the interstellar medium. The implications were profound. Imagine believing you have mapped an entire lake, then discovering the lake is actually part of an enormous river system. The water still exists. The lake still exists. But your understanding of its role changes completely. Researchers increasingly suspected something similar. The local bubble might not be a standalone feature. It might be one component of a much larger interstellar network. That possibility transformed the mystery once again, because networks behave differently than isolated structures. Events occurring far away can influence local conditions. Changes propagate. Connections matter. The galaxy becomes more dynamic, more interconnected, more difficult to simplify. Then another complication emerged. Astronomers began studying nearby interstellar clouds in greater detail. These clouds are extraordinarily diffuse by earthly standards, yet compared to the surrounding cavity, they contain significantly more material. The solar system itself appears to be moving through one such cloud. At first glance, this seemed unremarkable. Clouds exist. Stars move. The interaction was expected. The details, however, proved intriguing. The cloud's properties did not always fit neatly into existing models. Its shape appeared unusual. Its magnetic environment appeared unusual. Its relationship to the local bubble appeared unusual. The deeper researchers investigated, the more questions emerged. Where had the cloud originated? How old was it? What processes shaped it? The answers remained uncertain. Again, the pattern was becoming familiar. Every apparent solution uncovered deeper complexity. Every completed puzzle revealed a larger one behind it. Voyager's observations repeatedly pushed scientists toward this realization. The darkness between stars was not becoming simpler. It was becoming richer, layered, interconnected, historically complex. Then researchers encountered another perspective shift, one that challenged a subtle but important assumption. For much of the investigation, scientists had treated interstellar space as something relatively stable, not static, but stable. Changes occur. Structures evolve, yet generally on timescales so vast that they appear fixed from a human perspective. Voyager hinted otherwise. Evidence increasingly suggested that interstellar environments may evolve more actively than previously appreciated. Not rapidly, not dramatically, but continuously. Shockwaves propagate, clouds interact, magnetic fields reorganize, particles redistribute. The galaxy is alive with slow processes unfolding over millions of years, processes still occurring today. This realization altered the meaning of many observations. The local bubble was not merely a fossil, it might still be evolving. The interstellar medium was not merely an archive, it might still be writing new chapters. The distinction was subtle, yet enormously important. Because active systems are harder to predict than historical remnants, a fossil tells a fixed story. A living system continues changing. Scientists increasingly suspected they were studying the latter. Then another question emerged, one with surprisingly existential implications. How typical is our neighborhood? The assumption had always been that the solar system occupies a reasonably ordinary region of the Milky Way. Not unique, not exceptional. Just another location among billions. Voyager's discoveries complicated that assumption. Perhaps our local environment is unusual. Perhaps the local bubble is unusual. Perhaps the cosmic ray conditions surrounding Earth are unusual. The possibility was difficult to evaluate. After all, humanity has direct measurements from only one stellar neighborhood, our own. The realization exposed a deeper limitation. We often assume local conditions represent universal conditions. Voyager was reminding us that such assumptions can be dangerous. The galaxy may contain environments radically different from our own. Different densities, different magnetic structures, different histories, different levels of cosmic radiation. The solar system's neighborhood might be only one example among countless possibilities. That thought expanded the mystery beyond the Milky Way itself. If local environments vary so dramatically, what does that mean for other planetary systems, for other Earth-like worlds, for life elsewhere? Suddenly, Voyager's measurements acquired new significance. The spacecraft was not merely characterizing interstellar space, it was helping define the environmental context in which planetary systems exist. A context that may differ enormously across the galaxy. The implications stretched outward again, larger scales, larger questions. For a moment, scientists believed they had finally understood the local interstellar medium. Then the evidence suggested something even more unsettling. The boundaries themselves might be illusions, not false, but incomplete. Every frontier Voyager crossed seemed to reveal another frontier beyond it. The heliopause concealed interstellar space. Interstellar space concealed magnetic architecture. Magnetic architecture concealed galactic history. Galactic history hinted at even larger structures still unseen. The pattern was unmistakable. Every answer led to a larger mystery. And the next mystery concerned something profound, perhaps the most important lesson Voyager had uncovered. The possibility that there was no final boundary at all, only deeper layers waiting to be discovered. Human beings love frontiers. We build stories around them. The edge of a continent, the summit of a mountain, the shoreline of an ocean. The boundary represents a promise. Reach it and understanding follows. Cross it and the mystery ends. Voyager's journey revealed something very different. The mystery never ended. Every frontier concealed another. Every boundary exposed a deeper layer. The pattern repeated so consistently that it began to look less like coincidence and more like a fundamental feature of reality itself. At first, the mission appeared straightforward. Reach the outer solar system. Study the planets. Mission accomplished. Then the heliosphere became the mystery. Scientists sought its boundary. The heliopause. The point where solar influence gives way to interstellar space. A clear frontier, or so they thought. Voyager crossed it and immediately discovered a new mystery. The darkness between stars. Then came plasma densities, cosmic rays, ancient supernova remnants, magnetic structures. The local bubble. Each answer expanded the investigation. None concluded it. The spacecraft had become trapped in a strange cycle. The closer it moved toward understanding, the larger the unknown became. This realization carried an uncomfortable implication. Perhaps the universe is not organized around final answers. Perhaps it is organized around layers. Imagine an ancient city buried beneath sand. Archaeologists excavate the first layer. Beneath it lies another city, older, different. They excavate again. Another layer appears, then another, then another. The deeper they dig, the more history emerges. Voyager's discoveries suggested reality behaves similarly. The heliosphere was one layer, interstellar space was another, galactic magnetic architecture was another, ancient stellar history was another. The investigation kept descending through hidden levels of structure, and every level altered the meaning of the level above it. Consider the heliosphere. At first it seemed like the central object, the destination, the boundary humanity sought. Now it looked different. The heliosphere appeared less like an ending and more like a shoreline, a local feature shaped by larger forces. The importance of the heliosphere remained, but its context had changed. The same pattern applied everywhere. The local bubble seemed significant until scientists realized it belonged to larger interstellar systems. Those systems seemed significant until evidence suggested they were influenced by even broader galactic structures. The scale kept expanding, and with each expansion came a subtle philosophical challenge. Where does explanation stop? The question haunted science long before Voyager launched. Ancient astronomers asked it. Physicists ask it today. The deeper we investigate reality, the more connections appear, the more structure appears, the more hidden layers emerge. Voyager was providing a remarkable example. The spacecraft travelled farther from Earth than any human-made object in history. Yet its greatest discovery may have been how much remained unseen. The farther it travelled, the larger the unknown became. Then researchers noticed something fascinating. The same pattern appeared throughout the history of science. Early astronomers believed Earth occupied the centre of everything. The solar system expanded the map. Then the galaxy expanded it again. Then other galaxies. Then galaxy clusters. Then the cosmic web. Every generation believed it had approached the edge. Every generation discovered another layer beyond it. Voyager seemed to be reenacting the same story on a smaller scale. The mission was not merely exploring space. It was illustrating a principle. Reality appears deeper than our initial descriptions, always. The realization transformed how scientists interpreted the darkness between stars. At first, the darkness looked empty. Then it appeared populated. Then structured. Then historical. Then interconnected. Each description was more accurate than the previous one, yet none appeared complete. The universe resisted simplicity, and perhaps that resistance contained an important lesson. Imagine reading a novel while only seeing one page at a time. Each page makes sense. Each page contains information, yet the full story remains hidden. Humanity may occupy a similar position. Voyager provided a few additional pages, a few glimpses. Enough to reveal complexity, not enough to reveal everything. The analogy resonated deeply among researchers. Because the spacecraft repeatedly demonstrated the limits of certainty, scientists could measure, model, infer. But every conclusion carried caveats. Every answer contained unanswered questions. The mystery persisted, not because science failed, because reality was richer than expected. Then another perspective shift emerged, one that expanded the implications beyond astronomy. Voyager's discoveries suggested that knowledge itself might possess boundaries. Not fixed boundaries, moving boundaries, frontiers that retreat as understanding advances. The more we learn, the larger the map becomes, and larger maps reveal larger unknowns. This realization was both humbling and inspiring. Humbling because certainty becomes difficult, inspiring because discovery never ends. The investigation continues. The frontier continues. The darkness continues, revealing new structures, new questions, new possibilities. For a moment, scientists believed they had identified the deepest mystery surrounding Voyager. The nature of interstellar space, the structure of the local galactic environment, the hidden architecture of magnetic fields. Then an even larger realization emerged. Voyager's findings were not primarily about interstellar space at all. They were about humanity, about perspective, about the way intelligent beings attempt to understand reality. The spacecraft had crossed physical boundaries. but it had also exposed conceptual ones. Limits in our assumptions, limits in our maps, limits in our imagination. And those limits pointed toward an even bigger question. A question extending far beyond the solar system, far beyond the Milky Way. A question concerning humanity's place within an unfinished universe. Because perhaps Voyager's greatest discovery was not what it found. Perhaps it was what it revealed about the nature of discovery itself, and that realization would lead the investigation into its final act. At first glance, the answer seems obvious. Voyager found interstellar space. That is the headline. That is the milestone. That is the achievement recorded in history books. The first human-made object to enter the space between the stars. An extraordinary accomplishment. And yet, after decades of analysis, that description feels strangely incomplete, because the farther scientists examined Voyager's observations, the less the mission appeared to be about a location. Instead, it seemed to be about a relationship between the solar system and the galaxy around it, a relationship humanity had never directly observed before. This distinction matters. Locations are static. Relationships are dynamic. A location can be mapped. A relationship must be understood. Voyager revealed the latter. The spacecraft showed that the solar system is not isolated, not sealed off, not drifting through emptiness. It exists within a larger environment that continuously influences it. Cosmic rays arrive. Magnetic fields interact. Interstellar pressure shapes the heliosphere. Ancient supernovae leave traces. The galaxy reaches into our neighborhood in countless subtle ways. The solar system is part of something larger. That realization may be Voyager's most important discovery. For centuries, humanity's understanding of space was shaped by separation. Earth was separate from the heavens. The solar system was separate from the stars. Stars were separate from one another. Distance implied isolation. Voyager challenged that intuition. The spacecraft revealed connections, invisible connections, persistent connections. Connections operating across scales almost impossible to visualize. The Milky Way began to resemble less a collection of isolated objects and more a network. A system. A vast environment through which energy, matter, and information continuously move. The idea transformed the meaning of the darkness between stars. The darkness was no longer merely a gap. It was a medium, a bridge, a place where interactions occurred. Imagine looking at a forest and focusing only on the trees. You might miss the soil connecting them, the fungi linking their roots, the water circulating beneath them, the hidden systems sustaining the entire ecosystem. Voyager revealed something similar about the galaxy. For generations, astronomers concentrated on the luminous objects, the stars, the nebulae, the planets. Voyager illuminated the medium connecting them, and that medium turned out to be far more important than expected. The realization altered how scientists thought about galactic evolution. Stars do not exist independently. They emerge from interstellar material. They enrich that material when they die. Future stars form from the remnants of previous generations. The process is cyclical, continuous. The darkness between stars participates in every stage. Without it, the galaxy as we know it could not exist. Voyager helped expose that hidden role. Then researchers noticed another profound implication. The solar system itself is temporary. Not temporary in a human sense, temporary in a cosmic sense. The heliosphere exists because of the sun. The local bubble exists because of ancient supernovae. The local interstellar medium exists because of countless earlier events. Everything is evolving. Everything is changing. The environment surrounding Earth today is not the environment that existed millions of years ago, nor is it the environment that will exist millions of years from now. Voyager's discoveries repeatedly reinforce this lesson. The galaxy is not a static backdrop. It is a living history of ongoing transformations. The realization felt almost geological. Continents move. Mountains rise. Oceans change. Human lifetimes are too short to notice most of it. The same principle applies on galactic scales. Structures evolve. Clouds interact. Stars are born. Stars die. Shock waves propagate. The universe remains in motion. Voyager provided direct evidence of that motion, evidence embedded in particles, magnetic fields, and plasma densities. Then another perspective shift emerged, one perhaps more philosophical than scientific. The mission demonstrated the extraordinary value of persistence. Voyager was never designed to solve these mysteries. Its creators could not fully anticipate them. The spacecraft was built to study planets, Jupiter, Saturn, the outer solar system. Yet because it continued travelling, entirely new discoveries became possible. The lesson was subtle but important. Exploration often reveals questions that cannot be predicted in advance. The most important discoveries are not always the ones we set out to find. Voyager embodies that principle. The spacecraft became an interstellar observatory, almost by accident, a cosmic historian, almost by accident, a detector of galactic processes, almost by accident. And through that transformation, it revealed something fundamental about science itself. Knowledge expands through contact with the unknown, not through certainty, not through assumptions, through observation, through curiosity, through continuing forward. The deeper meaning of Voyager's mission began to crystallize. The spacecraft was not simply exploring a region, it was extending humanity's senses, carrying our instruments into environments previously inaccessible, allowing reality to speak for itself. And reality spoke in surprising ways. The darkness was not empty. The boundary was not simple. The galaxy was not disconnected. The history was not forgotten. Every assumption became more complicated and more interesting. For a moment, this seemed like the ultimate revelation, the true lesson of Voyager: interconnection, galactic context, the hidden environment surrounding the solar system. Then an even larger implication emerged, because if Voyager transformed our understanding of one small corner of the Milky Way, what hidden realities remain undiscovered elsewhere? The question was impossible to ignore. Humanity had sampled only a tiny fraction of interstellar space, a microscopic fraction of the galaxy, an infinitesimal fraction of the universe. The unknown remained immense, perhaps overwhelmingly immense. And that realization shifted the focus one final time, away from Voyager, away from interstellar space, toward ourselves, toward what it means to exist inside a universe whose true scale remains largely unexplored. The final mystery was no longer out there. The final mystery concerned our place within it. Human beings are map makers. Long before telescopes, long before spacecraft, long before written history, we drew boundaries, named places, organized the unknown into something understandable. A map is more than a tool. It is a declaration, a statement that reality can be described, measured, known. Every civilization has created them, every generation has trusted them, and every generation has eventually discovered that the map was incomplete. Voyager's journey belongs to that tradition, because in many ways the spacecraft exposed the limits of one of humanity's oldest habits, the belief that our maps accurately describe reality. At first, the solar system itself was the map, the sun, the planets, a relatively orderly structure extending outward into darkness. Then the heliosphere appeared. The map expanded. Then interstellar space. The map expanded again. Then magnetic architecture. Then the local bubble. Then ancient supernova histories. Each discovery added territory. Each discovery revealed previously hidden layers, and each discovery carried the same message. The map was not wrong. It was unfinished. That distinction is important. Science rarely replaces one complete picture with another. Instead, it gradually enlarges the picture. What once seemed comprehensive becomes local. What once seemed final becomes partial. Voyager demonstrated this process repeatedly. The spacecraft did not overturn our understanding of the solar system. It placed the solar system into a larger context, a deeper context, a more complicated context. The pattern extends throughout the history of astronomy. Ancient observers mapped the stars. Then came the realization that planets existed. Then solar systems. Then galaxies. Then galaxy clusters. Then the cosmic web. Each step enlarged the territory. Each step increased the unknown. Paradoxically, greater knowledge often reveals greater ignorance. Voyager became a powerful example of this paradox. The farther the spacecraft traveled, the more obvious the limitations of existing maps became. Researchers repeatedly encountered phenomena they had not anticipated. The heliopause behaved differently than expected. Magnetic fields behaved differently than expected. Cosmic rays behaved differently than expected. Even the local interstellar medium behaved differently than expected. Reality proved richer than prediction, again and again. This was not a failure of science. It was evidence of science working exactly as intended. Assumptions confronted observations. Observations refined assumptions. Knowledge evolved. Yet the process carried an important psychological challenge. Humans naturally seek closure. We like final answers, definitive conclusions, completed maps. Voyager offered something else, a reminder that exploration often produces more questions than answers. The deeper we look, the larger the mystery becomes. Imagine standing on a hill overlooking a forest. At first, the landscape seems comprehensible, a simple collection of trees. Then you enter the forest. Paths appear, streams appear, valleys appear. Entire ecosystems emerge. The closer you get, the more complexity you discover. The universe appears to operate in much the same way. Distance creates simplicity. Proximity reveals structure. Voyager moved closer to a hidden layer of reality, and that layer proved astonishingly rich. Then another realization emerged. Perhaps the limits exposed by Voyager are not merely technological. Perhaps some are conceptual. Human understanding depends heavily on categories: inside and outside, star and interstellar space, boundary and environment, cause and effect. These categories are useful, essential even, yet Voyager repeatedly revealed situations where the categories blurred. The heliopause was not a simple line. The local bubble was not a simple cavity. The darkness between stars was not empty. Reality resisted neat classifications. The lesson echoed across multiple disciplines. Biology encounters it. Geology encounters it. Physics encounters it. Nature often behaves as a continuum rather than a collection of separate boxes. Voyager's discoveries reinforced this idea. The boundaries we draw help us understand reality, but reality itself does not always recognize them. This realization introduced a deeper question. If our categories are imperfect, how many hidden assumptions remain embedded within our maps? The question is difficult, perhaps impossible. Every generation inherits frameworks from previous generations. Most work remarkably well. Some eventually require revision. The challenge lies in identifying which is which. Voyager helped expose several. The spacecraft showed that interstellar space is not emptiness, that magnetic fields are more important than once assumed, that local galactic history matters, that cosmic environments influence solar systems. How many additional assumptions remain waiting to be challenged? No one knows. And that uncertainty may be one of the mission's most important legacies, because uncertainty is not merely a limitation, it is an invitation to continue exploring, to continue questioning, to continue extending the map. The history of science suggests that every frontier eventually reveals another. The edge of Earth revealed oceans. The oceans revealed continents. The solar system revealed the galaxy. The galaxy revealed a universe filled with galaxies. Voyager revealed interstellar space. What will the next frontier reveal? The question remains unanswered. Perhaps it always will. Then comes a final perspective shift, one that transforms the entire story. Throughout the mission, scientists focused on what Voyager detected: particles, fields, densities, structures. Yet behind every measurement lies a more profound achievement. A species on a small planet managed to send a machine beyond its own stellar neighborhood. A species that evolved beneath one star extended its awareness into the darkness between stars. The accomplishment is extraordinary, not because Voyager solved every mystery, because it demonstrated that the mysteries can be investigated at all. The spacecraft transformed the unknown into something measurable, and in doing so, it expanded the boundaries of human experience. Yet even after everything Voyager revealed, the unknown remains vast, almost incomprehensibly vast. The maps have grown. The mysteries have grown faster, and that realization leads directly to the final question, not what Voyager found, but what its discoveries ultimately mean for science, for humanity, and for our place within a universe that appears larger and stranger every time we explore it. For nearly half a century, Voyager has been traveling away from home, year after year, billion mile after billion mile. The spacecraft continues moving through darkness that no human being will ever personally witness. Its signals grow weaker. Its power slowly fades. Its instruments fall silent one by one. And yet somehow the mission has become larger than the machine itself, because Voyager's greatest discovery may not be any particular measurement. Not a plasma density, not a magnetic field, not a cosmic ray. Those were clues. Important clues, but clues nonetheless. The deeper discovery concerns something more fundamental, the nature of the unknown. At the beginning of this story, the mystery seemed straightforward. Where does the solar system end? A simple question. A reasonable question. One boundary, one answer, one crossing. Instead, the investigation revealed a cascade of hidden layers. The heliosphere concealed the heliopause. The heliopause concealed interstellar space. Interstellar space concealed magnetic architecture. Magnetic architecture concealed ancient galactic history. Ancient galactic history hinted at larger structures beyond our immediate neighborhood. The mystery expanded faster than the explanations, and perhaps that is the most important lesson of all. Human beings often imagine knowledge as a process of reducing uncertainty. a shrinking circle of ignorance. Voyager suggests something subtler. Knowledge expands uncertainty. Every discovery reveals additional territory. Every answer uncovers deeper questions. The circle grows larger, and so does its boundary with the unknown. The mission's history illustrates this beautifully. Scientists expected a boundary. They found an environment. They expected emptiness. They found structure. They expected isolation. They found connection. Again and again, reality proved more complicated than anticipated, more interconnected, more layered, more alive with hidden processes. The darkness between stars turned out not to be dark in any meaningful sense. It contains matter, history, magnetic fields, cosmic rays, ancient scars, invisible rivers of energy. The apparent void became a landscape, and landscapes invite exploration. Yet perhaps the most striking realization concerns scale. Throughout the investigation, the perspective kept shifting. A spacecraft became a solar system story. The solar system became a galactic story. The galaxy became a question about the nature of reality itself. The pattern was impossible to ignore. Every scale connected to larger scales. Every local mystery reflected a broader context. The implication is profound. Nothing exists in isolation. Not planets, not stars, not solar systems, not even galaxies. Everything belongs to larger structures, larger histories, larger environments. Voyager revealed those connections with extraordinary clarity. Then comes the realization that may be most difficult to absorb. Humanity has explored only a tiny fraction of what exists, a tiny fraction of the solar system, an even smaller fraction of interstellar space, an infinitesimal fraction of the Milky Way. And the Milky Way itself is only one galaxy among hundreds of billions. The scale is overwhelming. Yet Voyager demonstrated something remarkable. The unknown is not inaccessible. It can be investigated. One measurement at a time, one observation at a time, one question at a time. That achievement may be the mission's deepest legacy, not certainty, curiosity, the willingness to continue asking questions even when the answers become more complicated, especially when they become more complicated, because reality repeatedly rewards that persistence. Then there is the spacecraft itself. Voyager 1 is now farther from Earth than any object humanity has ever created. Its signals require more than a day to arrive. The spacecraft exists in a realm so distant that ordinary intuition fails completely, and still it communicates. Still, it sends traces of information back across the darkness, a mechanical survivor carrying evidence from a place no human has reached. There is something almost symbolic about that. Voyager is not merely travelling through interstellar space. It is travelling through the frontier of human understanding. The spacecraft keeps moving. The map keeps growing. The mystery keeps expanding. And perhaps it always will, because every generation inherits a universe larger than the one known by the generation before it. Every generation discovers hidden layers beneath familiar assumptions. Every generation learns that the darkness contains more than expected. Voyager's journey is simply one chapter in that larger story, a story that began long before the spacecraft launched, and a story that will continue long after its final signal fades into silence. Eventually, Voyager's instruments will stop working, the transmissions will cease. The spacecraft will continue drifting through the galaxy alone, a silent artifact moving among the stars. Its mission completed, its discoveries preserved, yet the questions it helped reveal will remain. What other structures exist beyond the local bubble? What other magnetic architectures shape the Milky Way? How many ancient histories remain hidden within interstellar space? How many layers of reality still wait beneath the ones we already know? No one can answer those questions today, and that is precisely what makes them valuable, because unanswered questions are not failures. They are frontiers. They are invitations. They are reminders that the universe remains unfinished from our perspective. Perhaps that is the real lesson Voyager carried into the darkness. Not that we finally understand the space between the stars, but that understanding is itself a journey with no obvious ending, a journey where every horizon reveals another horizon beyond it. And somewhere far beyond the edge of our familiar maps, Voyager continues drifting through a region that once seemed empty, a region now known to contain traces of ancient explosions, invisible rivers of magnetism, and echoes from stars long dead. Perhaps future explorers will uncover deeper layers still. Perhaps they will discover that the structures Voyager revealed are merely the surface of something even larger. Maybe the darkness between stars is not a void at all. Maybe it is one small part of a hidden architecture stretching across the galaxy, or perhaps across the universe itself. If that is true, then Voyager's greatest discovery was not what it detected. It was the realization that the mystery remains, and that beyond every boundary we cross, another one is waiting.